ईयर का
अच्छा
35
साइड पे
प्रोग्राम्स
डाल
हैं।
देते हैं।
हाँ, साइट पे आ जाता है।
बस बस और उसको पॉपुलराइज कर दीजिए खूब आप, और बढ़िया बनाए।
हाँ, वो करते हैं, जैसे हर बार उससे 15 दिन पहले या 1 मंथ पहले
Good morning. Today
We are having a one-day workshop on Raman spectroscopy and its application in Earth observation. I am Dr. Shashi Kumar, a scientist in Indian Institute of Remote Sensing, and the today's workshop schedule is after this inaugural function, there will be a lecture by Professor S.N. Thakur on laser Raman spectroscopy and its applications. Then the second lecture will be delivered by Dr. Ranjan Kumar Singh on fundamentals of Raman spectroscopy. After that, there will be a lecture by Dr. Mamta Chauhan on geological applications of Raman spectroscopy. And then there will be another lecture by me on applications of Raman spectroscopy in Earth observation. And the last talk will be in afternoon from 2:30 to 4 o'clock. That will be on Raman spectroscopy and its application in Raman LIDAR for the Earth observations, atmospheric science perspective. That talk will be delivered by our guest, Dr. Som Kumar Sharma ji. Now I request Group Director G Top G Group of IIRS to provide her remarks on this workshop.
Thank you, Dr. Shashi. Dr. R.P. Singh, Director IIRS and Director STEEP. Dr. Som Kumar Sharma, who is also the faculty in this program from PRL. Dr. Shashi, the course coordinator. Dr. Mamta, faculty who is present here in the Edu studio. And the dear course participants who have connected with us from all across the country, from various central state institutions, as well as students from the academic institutions. A very warm welcome to you on this special occasion of a very special workshop on Raman spectroscopy and its application in Earth observation. Just to tell you before about this workshop, what was the purpose of it? I'll just give you a glimpse of our distance learning program, because this is the workshop being conducted under the IIRS distance learning program. The distance learning program journey of this program started way back 17 years ago in 2007, where we started this program to augment or supplement the in-house training program, as well as the academic programs across various institutions across the country, academic institutes, to provide a basic understanding at that moment of time on the basics of remote sensing, GIS, GNSS. And as the time grew, this program also evolved with time and it took new dimensions. So not only training in the basic fundamental courses of remote sensing and GIS, we started expanding to train about the various applications of the remote sensing or the Earth observation technology. Along with it, we started giving awareness programs. We took this course as an step, as a platform to give exposure to the new technologies which were evolving in time. And in this context, this workshop is also as a part of this journey, where we are trying to take this platform and try to give an exposure on a very upcoming technology, the future technology, that is Raman spectroscopy and its application in Earth observation. Raman spectroscopy, if I say so, is an analytical tool for gaining valuable insights into the molecular composition of material and its application in Earth observation, which has recently started, has opened up new frontiers in environmental monitoring, climatic studies, and diverse application in earth sciences. I mean, we haven't seen many applications, just emerging technology. Raman spectroscopy is not a new technology, it's an old one and had applications in various other domains, but in earth observation, it started developing. So it has a very significant benefits over the various infrared spectroscopic techniques, like it has the capability to analyze the solid, liquid, and gases. And recently, it has been also used in planetary exploration, which will be told to you, or which will be as a part of the, there is a lecture on it, how it has been used in the space planetary exploration. So I hope that you will benefit from this workshop. And in this workshop, I'm glad to see that a large number of participants from across various sectors have joined us, a total number of 3,226 participants, where there are student community is around 2,712. Working professionals are around 366, and from other sectors who are curious to learn this technology are around 148. So I once again welcome you all in this workshop, and I hope you will interact and have a good learning experience in this workshop. Thank you.
Thank you, madam, for your remarks. Now, I request our guest, Dr. Asom Kumar Sharma ji, to provide his remarks on the workshop.
Thank you, IIRS, and Professor R.P. Singh, Professor Sasi Kumar ji, Professor Sefali madam, and Mamta madam. It is truly honor for me to be with you all on this very specialized workshop, which is on a very important, innovative, and full of science, I will say. That is a tool, Raman spectroscopy. Everybody knows that Raman revolutionized this field by discovery of the Raman effect. And that Raman effect has penetrated in each and every field of the life, whether it is our atmospheric sciences, which is our close to heart, space science, our mandate, planetary sciences, biological sciences, forensic sciences, forestry, agrometry, and in agriculture. And this list is not exhaustive. There are various other fields where this tool and technique, I will say, because spectroscopy is a tool, beautiful tool, that is being utilized very effectively for the betterment of the societal perspectives. Just I will say like that, by using Raman LiDAR, we are able to detect several species in the atmosphere very precisely, and we are able to quantify. Similarly, in other fields also, it has a very wide scope as well as the precision, which is always associated with the spectroscopic studies. That is going to be, I think, discussed today in this full day workshop. So I will congratulate IIRS and the full team of the IIRS under the effective leadership of Professor R.P. Singh, Director IIRS, and to all the audiences and the court participants who have joined, or you can say registered for this workshop. They will immensely benefit by today's deliberation. I wish all the best, and I am thankful for me. I am thankful to IIRS for giving me this opportunity to be present here in person to interact with you all, though you all are joining online. So afternoon, I'll be with you with more ideas and thoughts how this spectroscopic tool and technique can be utilized effectively for atmospheric science investigation. Thank you very much and wish you all the best. Good luck.
Thank you, sir. Now I request a respected director, sir, for his address on this workshop, and I request to formally inaugurate this workshop also.
Thank you, Dr. Sasi. Good morning to all of you. Professor S.N. Thakur, ex-professor of physics, Department of Physics, BHU. Professor Ranjan Kumar Singh, professor of physics in Department of Physics, BHU. Professor Som Kumar Sharma, the professor PRL. Mrs. Sipari Agrawal, Top G of IIRS. Dr. Shashi, Dr. Mamta, and all the participants and coordinator of this course. You're all welcome to this online course of IIRS Dehradun under distance learning program. This particular topic, which this workshop is going to be there on Raman spectroscopy and its application on Earth's observation, is a relatively new topic to us, as we conduct many courses every year online and offline both. But this is one of the unique and new topic, because this technology is although very popular in many applications, as Dr. Som already suggested, but this technology is new as far as space research and planetary exploration is concerned. We know that satellite remote sensing started from 1957 when the Sputnik launch took place. And we found that the space platforms are the very good place where we can see the pictures of Earth over the large region and beautiful synoptic coverages. And all started in 1960 with IIRS launch, where atmospheric science, meteorology, and such kind of observations started taking place. Later on, with the development of Landsat, many new satellites, and this technology grew up, and it has become a operational technique for resource mapping, atmospheric sciences, ocean application, geology, groundwater, call anything, environmental monitoring. So it has reached to its maturity and being used by various stakeholders from government to industry in different applications. The principle on which this remote sensing works, the traditional remote sensing, which I'm talking about, is elastic scattering, where the incident light scatters with the matter, and the scattered light has the same frequency of the what it was incident upon it. The another principle of scattering, what we call inelastic scattering, Raman is one of its example, where the scattered light is not of the same frequency, but there is shift in the frequency. And this phenomenon was known in 1928, and Sir C.V. Raman was given Nobel Prize in 1930. Here, the molecular interactions are bit different than what traditionally happen from elastic, and it start giving some unique and definitive features of the chemical composition of material and many things. It has a unique advantage that many times of whenever there are possibility of organic molecule or molecule with having life association in planetary system, this technology is capable of doing it. That is why it is becoming popular nowadays in the Earth observation and planetary explorations. The very challenging fact about this technology is that the scattered light, what we get out of scattering, is of very small quantity. There are very few photons which come in which are Raman in nature, which changes their frequency as compared to our elastic scattering, and you get a huge signal. Because your signals are very small, the ground instrumentation and the lab-based experimentations are very popular and well known. But when you have to do from the satellite or from the distance, obviously, the one has to take care of the energetics and see how to collect the small signals. That is why it is popular now in rover kind of system. And the first of its kind rover, Sherlock rover, I mean instrument on Perseverance rover, is put into there in Mars, where it is this Perseverance rover is moving, and Sherlock, which is a Raman spectrometer, works from the incident radiation of deep UV laser, is working and providing valuable data of the past history, aqueous history of Mars. This is one of its own kind. The ExoMars mission also has planned similar thing, and it is going to be launched in 2028. And future, many space exploration would be based upon this principle of Raman spectroscopy. So we thought that we have to conduct a program on this basic fundamentals of this technology, so that we are aware of it, and we can use this technology for our applications. I'm thankful to the professors who has agreed to give talk, Professor Asan Thakur, Professor Ranjan Kumar Singh, Professor Som, who are expert in their field. So Professor Sasi and Dr. Mamita, they are doing excellent work and pioneer work in their own field. So today you are going to see that their experiences and how this technology works, what are the observations, and I am very sure it will be very interesting to all of you. Thank you very much, and I wish best of the success of this program. Thank you.
Thank you, sir, for
the valuable information provided by you on Raman spectroscopy and its application, particularly in the planetary sciences. Now we are going to close this inaugural ceremony. The workshop has been inaugurated now, and very soon we will start the in next 5 minutes we will start the lecture of Professor S.N. Thakur on laser Raman spectroscopy and applications. Wait for next 5 minutes. Thank you. due to some technical issue, we were not able to connect. Now we are going to start the first lecture by Dr. S.N. Thakur. Sir, please start the lecture, sir.
Namaskar and good morning to all of you. I am very thankful to the members of the organizing committee of this workshop who have given me the opportunity to talk to such a large, huge audience. You know, the complication which arose is because of me, and I must make it very clear at the outset that I'm not used to this kind of talking. I am used to talking to audience where I can see the faces, and from the response of the faces, I can modify my talk so that I'm understandable. So this is kind of a monologue, and it is going to be like telling a story. Now, in this story, I will tell you about the Raman effect and about its applications in detecting molecules on the Earth, in the atmosphere, and also on Mars. Now, before telling you this story, I must tell you that I am associated with Banaras University in 1958, and I carried out research in laser and spectroscopy laboratory, which was started in 1939 by Professor R.K. Asundi and is still continuing. So Professor Raman was a university professor since the very beginning, since 1916. And there are many stories which I heard from people about Raman, although I never got an opportunity to see him in person. The first impression of Sir C.V. Raman was given to me by my father, who was a school teacher in Sarnath, where I went to school. And he told me that in 1941, he had heard Professor Raman speak to an audience of several hundred students and teachers in Banaras Hindu University in the physics department. Now, those of you who get a chance to visit the Banaras University, it is a huge campus, and the building of physics has a very long, in fact, it has two very long verandas, and these are about 60 feet long and about 20 feet wide. So because Professor Raman had come for the Silver Jubilee celebration of Banaras University in 1941, and my father was a student of intermediate science at that time. So when Sir Raman saw that the number is so large, instead of giving his lecture in the lecture hall, he decided to lecture in the veranda. So all the teachers sat on either side of the veranda along the length, and Professor Raman would walk along the length of the veranda and speak about scattering of light and the Raman effect. The students were standing on all sides of the veranda, and there is a big quadrangle in which there was a big audience of students. So my father told me that because his English was not very good, so he could not understand every word that Professor Raman said. But with his hand gestures and gesture of his intense eyes, he was able to convey the phenomenon of scattering of light by molecules, and to some extent, what is Raman effect. So this was the first impression. And, you know, I had seen the photo of Sir Raman in school in my book, which was like a god with very intense eyes. So I was very much motivated by his personality. Later, I heard about him from another teacher, which I will describe later. But if we can go to the next slide, please. You see, Sir C.V. Raman had a very interesting personality. And he worked not with light. His initial work was with surface tension, and then he worked on musical instruments. And after 1920, he worked on light. And in light also, he worked on a variety of phenomena. he worked on the color of flowers, color of butterflies, color of diamonds, and he worked on X-rays. Now, there are some statements which are given in this slide made by some very famous people. The one that you see in blue is made by Dr. S. Ramakrishnan, who was director of Indian Institute of Science in 80s, and he had come to our department on the occasion of Golden Jubilee of Raman effect, that is 50 years of Raman effect, and he described in his lecture what is Raman, how was Raman. He says, according to the modern view of science, nature can only be described. It cannot be explained. Like many extraordinary natural phenomena, Raman can only be described. He defines explanation. You know, there are certain things which I will try to show you later in this lecture, which show how interesting his personality was. Einstein wrote about the impression that Raman effect made on him. He says, C.V. Raman was the first to recognize and demonstrate that the energy of photon can undergo partial transformation within matter. I still recall vividly the deep impression that this discovery made on all of us. Now, as I told you, he was associated with Banaras Hindu University, and he participated in its inaugural function. And whenever he came to BHU, he gave a lecture. The first lecture that he gave in 1961 was on mathematics and some new paths in physics. Then, if you can Google, he gave the chief guest lecture on the University BHU convocation of 1926. And he had very high regard for BHU and its founder, Pandit Madan Mohan Malviya. So he says, I see to BHU which seeks to bring together our ancient culture and knowledge, which is a great instrument for uplifting our country and for connecting together the people of India into a single nation. I see it as a center of learning with the greatest potentialities for the intellectual, moral, and material welfare of our countrymen. Now, see, this is very small part of that big lecture, and especially the young people who can Google and read this lecture is very motivating. He talks about how young people are very important in science, and he says that the duty of the older people, teachers like us and others, is to encourage young people, because the breakthroughs are to come from young people. And I think many among this audience are very young. And I will strongly suggest that some of you please read this lecture. The second slide, please. Second slide. Now here you see I'm very thankful to Professor R.P. Singh, who greatly helped me make my haphazard slides into a streamline so that I can make some specific remarks. So you see, these are the cornerstones of this talk. The Raman effect was discovered on 28 February 1928 by Sir C.V. Raman and K.S. Krishnan. And there is a huge group of research scholars was working with him, and all of them had contributed. We will come to it later. Raman spectroscopy is based on the phenomena of inelastic scattering of light by molecules. where a photon exchanges a specific amount of energy with molecular vibrations. Now you see, molecules are different from atoms in the sense that atoms have only electronic energy, that it depends upon the orbital. If the electronic orbital is higher, then the energy of the atom is larger. And if in the case of molecule, in addition to electronic energy, that is the charge cloud, there is also the vibrational energy. And a molecule with n electrons has 3n-6 different modes of vibration. So that a diatomic molecule, a molecule consisting of two atoms, has only one mode of vibration. But a molecule like H2O, water molecule, with three atoms has how many? Four modes of vibrations, or three modes of vibrations. In the case of benzene molecule, which is a molecule with 12 atoms, there are 30 different modes of vibrations. So one quantum of vibration energy is added to the photon in an inelastic collision, and its energy increases so that the frequency shift is towards the higher side. Its frequency becomes more. If the molecule snatches energy from the photon by one quantum vibration, then the photon wavelength is increased, its frequency is decreased, and there is a red shift in this. So the Raman spectrum appears as a shift in the spectral line, which is used to excite the Raman spectrum. The process has a very weak cross-section with only one. If there are 1 million collisions between photons and atoms, they are all elastic collisions in which the photon energy remains unchanged, the wavelength of the light remains unchanged, but only one is inelastic, in which it can increase in energy and decrease in energy, or decrease in energy. So the intensity of Raman band is extremely weak, and therefore it takes, it used to take a very long time. We'll see to it in the later part of the lecture. The development of lasers in 1960 significantly expanded the application of Raman spectroscopy. Now you see, when I joined the spectroscopy department in 1962, we had an experiment on Raman effect. And it used to take several hours of exposure to get the Raman bands and do the analysis. We used CCl4, carbon tetrachloride, as the molecule to get Raman spectrum. And I was told by my teachers that, you know, Raman spectroscopy has no future because no one has so much time to devote in taking the photographs. But then the lasers appeared in 1960 and it changed the whole scenario. Now, Raman spectroscopy is not just a tool, it is a science. It has applications in space, it has applications in biology, it has applications in medical science. I mean, any walk of life, you are activity, human activity, there is application of Raman spectroscopy. So can we go to the next slide, please? Next slide, please. Next slide, please. You see, in this lecture, Professor Rapi Singh had divided it into three main parts. That is basic physics of Raman effect, then historical context and personal insights, and then advanced techniques and applications. So next slide, please. So you see here, I have shown you these photographs. On the left side, the block that you see, there is a lamp which gives white light, and there is a prism which breaks it into a spectrum. Now, this lamp is not white light, it's a mercury lamp, let us say, and therefore it gives discrete spectral lines. Now, the prism, what it does is that it spreads these spectral lines into different spatial positions, and then you select one of the lines to excite the Raman spectrum in a cell, which is shown on the right-hand side. Now, you see the intensity of the lamp is very high, but the intensity of the spectral line, which is used to excite this Raman spectrum, is very weak because it has to be selected through a slit. The whole spectrum is dispersed over a wide range, and you make a small slit and take the blue line, and then what you find is that there are 3 beams emerging from this liquid sample. The red one is the Stokes Raman line, in which the molecule has snatched 1 quantum of energy from the photon. RY, the blue one, whose wavelength is unchanged, is the Rayleigh scattering. And then at the lower side, the violet one is Stokes Raman line, in which photon has snatched 1 quantum of vibrational energy from the molecule, and it has increased its frequency. Now at the top, it is said that the ratio of R to RY is 1:10 to the power 27, which means out of 10 to the power 27 photons of blue incident on the liquid sample, only 1 will be either Stokes or anti-Stokes scattered. So it is very weak, very weak. Now, compared to this, at the bottom, you see there is a laser beam, the green laser beam, and the intensity of this light is very large compared to the intensity that you saw in the blue, which had been obtained from this dispersion of the mercury lamp. And therefore, the 3 beams which emerge out, the anti-Stokes, which is blue, the Stokes, which is red, and the Rayleigh, which is green, they are all very intense. And therefore, the Raman spectrum can be recorded very easily. I will show you later in a slide the examples of how long it takes in a conventional thing where you use a prism to disperse the lamp light and a laser to record the Raman spectrum. Next slide, please. You see, in this picture, I will like to have your attention to the top of this picture is Lord Rayleigh. And on the left side, at the bottom is Sir C.V. Raman. And then there is a story about it. In 1907, Raman had just joined the finance service, and he was in ISCA, and he wrote a paper on surface tension, which was published in Philosophical Magazine. And this paper happened to be next to the paper published by Lord Rayleigh on the sensitivity of ear for different kinds of sound. And Lord Rayleigh was so impressed by Raman's presentation of surface tension paper that he wrote a letter, personal letter to Raman. He didn't know that Raman is not a professor, so he addressed Raman as Professor Raman, and then wrote very highly about the content of his paper. Raman was so impressed by Lord Rayleigh that throughout his life, he remained a devotee of Rayleigh. He liked Dr. Rayleigh very much. So the discovery of Raman effect is related to the work of Lord Rayleigh. You see, those of you who get a chance to go to this region which is around Greece, there is a sea, Mediterranean Sea, and Mediterranean Sea is deep blue. The color is very blue. It is very different from the color of Hind Mahasagar. It is very different from the color of Atlantic Ocean or Pacific Ocean. And this was a mystery why the color of Mediterranean Sea was deep blue. Now, Lord Rayleigh in 1910 had explained it in terms of the reflection of the sky, because you know, the sky is blue. And why the sky is blue? Because the sunlight, which is white, it gets scattered by dust particles in the Earth's atmosphere. And there is a rule of scattering. The strength of scattering is inversely proportional to the fourth power of the wavelength, which means blue light will be scattered many more times than the red. And therefore, the proportion of blue light is scattered by these particles is much more than any other, and that is why it looks blue. Now, this was known, and Lord Rayleigh said that, you know, it is a simply reflection of this blue color of sky, which makes the color of Mediterranean Sea blue. Now, Raman got a chance to go to England in 1921, and in those days there were the sea voyage. He went by sea, and you see, Raman, you know, Raman was a very interesting person. He always carried in his pocket a spectroscope, a visual, you know, it is a simple cylindrical tube in which there is a prism, and if you align it towards any source, you can see the spectrum of that source. So that is called a linear spectroscope or something. And he also carried a Nicol prism. You know that Nicol prism, what it does is it polarizes light. And if there is polarized light, by rotating the Nicol prism, you can cut the polarization and get no light. So when his ship arrived in the Mediterranean Sea, he looked at the sea, and you know, from the sea surface, the light is scattered or reflected. Now it reflected at different angles. Now there is an angle which is called Brewster's angle. So if the light is incident on the ocean surface at Brewster's angle, the reflected light is totally polarized, totally plane polarized. And the proportion of this light which is reflected is between 2 to 4%. So he used his spectroscope and saw the blue light. And then he realized that it is Brewster angle, therefore it will be polarized. So he used the Nicol prism, and then he cut off the reflected light from the vision. But still then, he saw a deep blue color. Now this deep blue color could not come from the reflected light. So it came from deep inside the ocean. And you know, that was a big surprise for Sir C.V. Raman, because he had proven his distant mentor wrong. He realized that, you know, the light which is coming from deep inside the ocean is the reason for the blue color of the ocean, and it is not the reflection of the sky. And when he returned to India, he conducted vigorous experiments on very, very much purified waters, and he studied the scattered light, and he wrote a monograph in 1922, which was called The Molecular Diffraction of Light. Now, this gave him the idea of Raman effect. I mean, this was the seed which germinated into a Raman effect after 7 years. See, he was also a professor in Calcutta University, And Sir Asutosh, who was the Vice Chancellor of Calcutta University, he organized a meeting to honor Sir C.V. Raman because he had been made Fellow of the Royal Society. And in that meeting, Raman said that in next 10 years, I will bring Nobel Prize to India. And that he did in 1928. So next slide, please. You see, this I will give a very simple explanation of Raman scattering. Now, look at the bottom of this slide. There are three blobs. There is a spherical blob with two lines, black lines at the top and bottom. So they represent metallic plates between which electric field can be applied. So it is like a condenser. So you see, when there is no field applied, the electronic charge cloud of the atom remains spherical. But suppose the upper plate is positively charged and the lower plate is negatively charged, then what will happen is, because the electrons are lighter, so the whole electron cloud will be shifted slightly towards the positive plate. And therefore, the center of positive and negative charges would be separated. Earlier in this sphere, the center of gravity of the spherical charge is at the same point as the nucleus. So the nucleus positive charge and electron negative charge, they are coincident. But when you apply a positive voltage to the upper plate and negative voltage to the lower plate, then the electronic cloud is elongated, and the two centers, the negative charge, center of negative charge goes up and center of positive charge goes down. So there is a dipole created. Now, if you reverse it, the direction of the dipole is reversed. Now, imagine that this is a oscillating electric field, so that you can change periodically this positive and negative. Then what will happen is this electronic dipole will start oscillating. So this is this is called polarization, and the polarizability of the molecule is the reason for Raman scattering. And this varying electric field is provided by the electromagnetic radiation. So at the top, you now see on the left-hand side, there is a green sinusoidal wave, which is incident on the charge cloud. And then the waves which appear on the right-hand side are of two kinds. At the top is the anti-strokes, the blue shifted, and at the bottom is the red shifted, and in the middle is the relay scattering. So the polarizability gives rise to inelastic scattering of Raman. This was the explanation given when the Raman effect was discovered in 1928. And it was, later we'll see, it was in 1931 that the quantum theory of this kind of two-photon process was discovered, because you will see that Raman process is a two-photon process. It is not a simple one-photon process. So next slide, please. So you see here, I have, as I described to you, I have tried to represent a pictorial, tried to give a pictorial description of what is electronic energy and what is vibrational energy. Now, on the there are two pairs. On the top, you see there is this benzene ring, and there is green charge cloud whose diameter is small, and then there is a radius or on the right hand side at the top is a bigger charge cloud. So this is electronic excitation. What happens is the molecules become big in terms of electronic charge cloud. The electronic charge cloud in the ground state is compact. In the excited state, it is a bigger diameter. So this is excitation, electronic excitation. Now, in the lower one, you see that the charge cloud remains unchanged. The charge cloud, the electronic charge cloud of the left-hand picture and the right-hand picture of benzene is the same. So the excited vibrational state The difference is that you see there is this arrow represents the motion of atoms, and you know these vibrations are. This is called a ring breathing vibration. What happens is the 6 carbon atoms move out and move in. The shape of this ring changes. It becomes bigger and smaller as the molecule vibrates. So this is vibrational energy, and this is also quantized. So because this motion is similar to the motion of our lungs, it is called a breathing vibration, as if benzene is breathing. So this is a Raman active vibration, and it is observed in the Raman spectrum of liquid benzene or vapor benzene. It is because of benzene molecules. So like this, there are 30 different vibrations, but all of them are not Raman active. Only some of them are Raman active, and you will get from internet, Google. If you Google, you get all these 30 vibrations and their different modes. But this is my purpose was to show that in this case, the electronic charge cloud doesn't change. There is only polarization. And this polarization occurs because of the vibrational motion, as I explained in the previous slide. So next slide, please. Oh, so you see, this is the this is the plate, photographic plate. At the top is the mercury lines of a mercury arc. There is no Raman effect there. This is simple. This is the spectrum of mercury as seen through the spectrograph. In the bottom one, the mercury light has been allowed to pass through liquid benzene. And you see that the things are changed because this exposure is very long. It is several hours compared to the one at the top. And therefore, the spectrum looks a little bit fuzzy. But what is important is the extreme line. If you see the extreme line at the top, it is 438 point. It is wrongly written 435.8. It is 435.8. Okay. So 435.8 nanometer. So on the right-hand side of this, which is towards the longer side, you see another line. And the gap which appears in the upper spectrum is now filled with another. So these are the Raman lines. The one on the right-hand side is the Stokes-Raman line, and the one on the left-hand side is the anti-Stokes-Raman line. And this was first seen by Professor K.S. Krishnan, and he see it visually, and then he photographed it, and then the Raman effect was discovered. Next slide, please. So you see here, you know, I mean, now the spectrographs have become sophisticated, but here you see a prism spectrograph on which Raman effect was discovered. You see, there are two stands, and these are lenses, and the lamp on one of them, and then there are lenses, and in between is the liquid benzene, which goes, the light goes through it, and this is the collimator arm of the spectrometer, which you see in the front of Professor C.V. Raman, and this light goes into the prism. This is a constant deviation prism, so that the light comes out of the prism at 90 degrees, and then there was a photographic plate which was put, and it was photographed on that. But before photographing, you can put a ground glass plate and then see the spectral lines visually. And that is what he is showing to a group of visitors. And you see how animated Professor C.V. Raman is. He was such a good teacher that he would he would paint a picture of anything, and he would make complex things very, very simple to understand. Now, there are a number of people who played very important roles in the discovery of Raman effect. K.R. Ramanathan had joined research group in December of 1921, soon after Sir C.V. Raman returned from his visit, and he was involved in purifying. The ordinary water has contained many other molecules and also dust particles and so on. So imagine the period of 1928 that they would purify water to make sure that there is nothing else in the water except water molecules. And that was not an easy thing to do. Even now this purification is not easy, but they try to make water as pure as possible so that they could get scattering only from water molecules, and that is what they did. They studied scattering from water, and Professor K.R. Ramanathan made very significant contributions in this regard. Next slide, please. So you see here there are two pictures. One is of Sir C.V. Raman. The other is of Professor D.D. Pant, who was a professor of a college, DSB college in Nainital, and single-handedly he had set up an experiment on a time-resolved spectroscopy using ordinary sources. And later on, when the lasers came, the government, the CSIR, RGC gave him grants, and it was much later in life. But he was a student of Banaras University. In fact, he was the student of first batch of spectroscopy under Professor R.K. Asundi. And the period of 1941-1942 was very turbulent in Varanasi. There were student agitations, and the government was trying to crush the agitation, and the students were being arrested. And he was a very bright student. So his professor, Professor R.K. Asundi, realized that if he is in Varanasi, he will be arrested and his careers will be destroyed. So he sent him to Sir C.V. Raman. And Professor Pant was such a nice individual that very soon he became one of the most favorite students of Sir C.V. Raman. Those people who have seen Sir C.V. Raman, and Professor Pant was one of them, and they say that it was not easy to talk to Sir C.V. Raman. If you make a slight mistake, he would he would be very he would try to correct you, and it would be very severe. So it was not easy to be a favorite student. So he got his PhD in Banaras, and then he went in 1960s. He went again to Sir C.V. Raman, and now he was in Raman Research Laboratory. So he said, "Raman, come, Pant, come. I will show you a photon." Professor Pant was surprised. How can one see a photon? So, but because he was his teacher, so he said, "Okay." So Sir C.V. Raman took him to a small room which was very dark, and they sat on chairs side by side. And after some time, Sir C.V. Raman looked towards the ceiling and said, look, there is a photon there." Professor Pant, first he didn't realize, he thought that maybe Sir C.V. Raman has become old, and that is why he's trying to say these things. And so he looked up, and when his eyes were accustomed to this darkness, he could see occasional specks of light in the ceiling. It was like those of you who have seen these fireflies, in Assam there are many fireflies, but in some places the fireflies are rare, and in the dark night if a firefly goes, you see a flash of light. So he could see a very dim flash of light, and then these were quite occasional and random. And then he realized that there were some cracks in that room, and whatever light entered through those cracks, that got scattered by the dust particles, and in the process of scattering, at certain points when your eyes your eyes were aligned to that direction, you saw that light. So this is to show how weak that scattering process is. And this had a purpose, because Raman effect was first observed by the eye and then photographed. Now to see this dim light of scattered Raman photons, your eye has to be sensitive to very, very, very weak intensity. And so the people would sit for several minutes or maybe half an hour or so in this dark room to make their eyes accustomed to the darkness, and then they will cover with their hands and go straight to the spectrograph and look at the spectrograph for the scattered photons. So this story or this photograph is just to emphasize how difficult it was for the Raman effect to be observed, and how difficult it was for the Raman effect to be observed and recorded. So next slide, please. You see, these are photographs. Now you see, in this there are three sections. The top one is a Raman spectrum, which has been photographed in 1 second. This is for benzene. The second one is photographed in 0.5 seconds. And the third one is photographed in 120 seconds. Now, these two, the top two, are liquid benzene. The density of molecules in the liquid is much higher than the density of liquids in the gas phase. So that is why the exposure time for the time of recording the Raman scattering in the liquid phase is easier than in the gas phase. The other thing is the slit width, how much light you allow to enter into the spectrograph. So the slit width is also changed. And so in the first case, the slit width is very small. In the second case, it is slightly larger. And in the third case, it is very larger. So to compare these spectra, which are recorded in seconds, and now it is possible to record in microseconds with very intense radiations. On the right-hand side, there are some statements made. It took many hours of exposure to photograph scattering from liquid benzene. The second one is, it required 15 hours exposure to photograph scattering from quartz crystal in Russia. Mandelstam was working with crystals while Raman was working with liquids. And Mandelstam also observed the scattering from crystals, and in Russia it is called Mandelstam effect. So because Sir C.V. Raman was so bright that as soon as the Raman effect was discovered, he called a press conference on 29th of February 1928 and announced that a new kind of light from molecules has been observed. And this was verified by a German scientist in Berlin. His name was Peter Prisingham, and it was this he did in June of 1928, and he was the first to call it Raman effect. So if you Google Peter Prisingham, and you will see that the effect is called Raman effect. So it was not Raman who called it Raman effect. It was Prisingham who called it the Raman effect, and it established that the Raman effect is real, because India was so poor in terms of equipment and money that people didn't believe that this kind of work can be done in India. So there was big competition. See, in one of the photographs, you saw the people who were present in the Nobel Prize ceremony, and Raman was there. Now, Professor Raman was so confident that in July of 1930, he had purchased 2 tickets for Stockholm, one for himself and one for his wife. He was confident that he will get the Nobel Prize. You know that the Nobel Prize is announced in November. So when the Nobel Prize was announced, someone ran to him and said, "Sir, you have received the Nobel Prize." Now, he was very particular about. He asked him, "Tell me, I'm alone or I have to share the bed with someone else?" And then they said, "No, you are the only one to receive the Nobel Prize." So he had worked very hard, and he had made it known to all the peoples of that time. He had published a paper quickly in Indian Journal of Physics, which was published from Calcutta, and sent the reprint to hundreds of scientists all over the world, and that established his priority in getting the credit for discovering Raman effect. So next slide, please. You see, here on the left-hand side are the energy levels. And as I told you, there are 2 sets of energy levels, the lower one and the upper one. So only one vibration of benzene, let us say, is shown. So you see 2 quanta of vibrational motion in the excited state and 2 quanta vibrational motion in the ground state. To make it very clear, I have shown the vibrational energy in the ground state to be larger than the vibrational energy in the excited state for the same mode. But it may be different also. It may happen that the vibrational energy of the same vibrational mode in the excited state is larger than its vibrational energy in the ground state. But what is important is that the transition, when we say that there is an electronic transition, it is in fact a band of lines which result because of transitions between different vibrational levels. Now you see, here we have a transition which is blue, and it goes from the ground state to the 2 quantum of vibrational state in the excited state. This blue arrow is a photon, blue photon, which takes the molecule from the ground state to 2 quantum of the excited state. Now, from this excited state, 3 things may happen. One is that it will be scattered as such, which will be Rayleigh scattering blue. The other is that it will be scattered at a photon of lower energy, which is seen as a green photon or a red photon. So these are Stokes-Raman lines. Stokes-Raman lines. Sorry, I'm sorry. This is fluorescence. There is actual transition, and so the lifetime of the upper state of the order of 10 to the power minus 8 seconds. So the molecule goes to the upper state and it stays there for 10 to the minus 9 seconds, and then it makes a transition to the lower state, and you get fluorescence. So the light may be unchanged or it may be shifted to the red side. This is called the fluorescence. Now here in the second case, you have transition from the ground state to the first quantum of vibrational state in the upper electronic layer, and then you have this again fluorescence level. Now, the reason I have shown transition only from the ground state, because the number of molecules, according to Maxwell-Boltzmann distribution, largest number of molecular density is in the ground state, ground vibrational state, and then the density increases as you go to the first quantum of vibrational state in the ground state or second quantum of vibrational state in the ground state. So in the fluorescence, the time that photon spends in the upper state is of the order of 10 to the power minus 9 seconds. In the case of Raman, it is a scattering phenomena. So imagine that the photon is passing by the molecule. Now, if we take the size of the molecule, the diameter of the molecule to be 1.5 angstrom, and imagine the photon with velocity of light passing across close to this molecule without being absorbed, then how much time it will spend? It will be, the calculation 5 into 10 to the power minus 19 seconds. So the interaction time between the molecule and the photon is 10 to the power minus 19 seconds. And therefore, this state, the upper state, which is involved in the Raman spectrum, is not a real state of the molecule. It is called a virtual state, and that is why it is shown by dotted lines on the right-hand side. So, what is shown here is that you see there is a violet or dark line which takes the molecule from the ground vibrational level to some level. This some level depends on the energy of the photon. So this the energy difference between the ground state of the molecule and the dotted line at the top is equal to the 1 quantum of photon which is incident on it. And then this photon is Rayleigh scattered or Raman scattered. If it is Rayleigh scattered, then you see it is coming to the same level from which it has gone. And if it is Raman scattered, it is shifted to the longer wavelength side. So the excitation is from 1 quantum of vibrational level in the ground state, and it goes to the top of the dotted line, that the virtual state, and from there, if it returns to the same level, it is Rayleigh scattering. If it stands to a higher vibrational level, its energy has been decreased by 1 quantum, and therefore it becomes a Stokes-Raman line. The important thing is that these two photons, the Raman photon, the incident photon and the scattered photon, whether it is Rayleigh photon or Raman photon, they happen to be together. For how long? For 10 to the power minus 19 seconds. So we say that this process is a 2-photon process in which 2 photons are simultaneously present in the vicinity of the molecule. So as I told you in the beginning, the theory of 2-photon absorption was discovered by, it was a theoretician, Maria Goeppert Mayer, who got this theory in 1931. And she was basically a nuclear physicist, and she got a Nobel Prize in 1963. So next slide, please. You see, there are the Raman effect that I have described earlier is called spontaneous Raman effect. That is, only photon is involved. Photon, you can have a blue photon, you can have a red photon, you can have a green photon impinging the same molecule and giving its characteristic Raman spectrum. So it is not important if it is a fixed frequency light. It is not important what color it is, and always you will get the Raman effect. But if the photon energy is close to the electronic energy difference of the molecule, then the scattering cross-section is increased manifold. The Raman spectrum becomes 10 to the power 4 or 5 times stronger than the spontaneous Raman effect, and this is called a resonance Raman effect. It has great importance in biological systems. Now here you see there is a retinol or something, I don't know this biological molecule, its name is given here. Its absorption spectrum is shown as a broad curve on the right hand side. If you see the first one, there is a broad curve in black, and this is the absorption spectrum of this biological molecule. Now, what happens is, if you use a continuous source, or if you use a tunable laser, you will not get anything. The fluorescence detection would give you a broad spectrum, which will be the absorption spectrum of characteristic absorption spectrum of this molecule. But if we use a source, laser source, whose frequency is very close to the electronic excitation energy, then you get strong Raman lines. So you see in the lower curve of this, you see discrete lines, and then you see the fluorescence. The fluorescence is on the right-hand side, is a broad fluorescence, and these are the Raman transistors. So the theory is very, very complicated. It involves interaction between, it is called vibronic interaction. That is the interaction with vibrational motion and electronic motion, and that causes this activity. So there are certain vibrations which are very strongly involved in resonance Raman scattering. And this is a very important tool in discovering the molecular vibrations of a complex biological molecule, which normally, if you take the spectrum, the fluorescence spectrum is, just broad, without featureless. So that is why Raman spectrum has got great importance in the field of biology, and there is now imaging processes which involves electronic detectors, which involves computer science to make image out of the colors that you get from the Raman scattering. Next slide, please. See, this is a very important process, CARS, coherent Raman scattering. It has got many uses. Now, what this process is, that instead of one laser, it uses two lasers. And one laser is fixed frequency. So here you see on the left-hand side in this energy level diagram, you see a fixed frequency, which is of orange color or yellow color, whatever you see. To me, it appears yellowish. So this, the arrow which takes the molecule to the virtual level is a yellow line. So this is one laser. So this is a fixed frequency laser. The other laser is a tunable laser, and you tune its frequency, tune till its frequency matches the difference between one quantum of vibrational excitation and this virtual level. So if the frequency of this second laser is shifted by one quantum of vibration from that of the fixed frequency laser, then when both of them are simultaneously incident, what happens is that the number of molecules in the upper vibrational level is increased. So normally, the largest molecular density would be in the ground state, but because of the presence of two lasers, the density in the one quantum vibrational level is very large. And now, if there is a Raman scattering from the fixed frequency laser from this level, the excited, one quantum excited vibrational level, then you see a Stokes line, which because it is seen by green. Now the importance of this is a 3-photon process, and as a result of this energy level diagram, the photon that emerges is this green photon, and it emerges like a laser beam. So it is a Raman laser. So it is directional and very intense. So coherent Raman scattering gives rise to a laser-like beam, and it has great advantage because if you send a laser beam into a flame, then what happens is, if it excites molecule in that flame, you can get a beam of light which is more intense than the flame itself, and you can see it and you can photograph it and you can so you see the idea is that this technique of KARS, coherent Raman scattering, is used to record the spectrum from hostile sources, sources like furnace or a flame or a jet engine, and it is used to measure the temperature of that environment by studying the vibrational energy distribution, the rotational bands of molecules in that. So the example is shown here. This is particular from a jet engine, and the band is the nitrogen band. So nitrogen molecules in that environment are excited by KARS, and then you get the band of nitrogen, which has these rotational lines. And from the intensity distribution of these rotational lines, there is a formula from which you can find out what is the effective temperature of that furnace. So this is used for this kind of detection. Next slide, please. You see, this is a example of imaging. And as I told you, I don't know very much about it, but this is a tablet which is used. We use normally we use what is that for pain, for headache, and all that. And aspirin is used for many things. So this is a special kind of aspirin in which there is caffeine and there is paracetamol, and these are seen. So the colors that you see. Aspirin molecules are shown by the blue color, the paracetamol molecules are shown by the green color, and caffeine molecules are shown by the there are very few on the this is a reddish color. So you can see very few molecules of caffeine, but you can enlarge this, and if you enlarge this, you see this one in the middle or the one at the right hand side, and this method is used for detecting distribution of molecules over an inhomogeneous structure, whether it is a tablet or whether it is a tissue and so on. So to compare this with electron microscopy, there are the images on the top right hand corner of a silicon wire which has been imaged by AFM and then by Raman. So the Raman can be used for imaging these small things, and now it has very important uses in nano materials, Raman spectroscopy. Next slide, please. You see, this is from a pamphlet, and it shows many kinds of spectroscopy, and I have described it. And what I would like to see is that on the top left hand corner, there are these plasmons, magnons, and phonons. So so Raman spectroscopy is used for phonon spectroscopy, magnon spectroscopy, and plasmon spectroscopy. Now, phonon is related with crystals, magnon is related with magnetic materials, and plasmons is related with these structures, the small structures, metallic structures in which there are electrons, and the spectrum that comes out of these nano structures is described by plasmons. So this is just to give you an idea how wide the applications of Raman spectroscopy are, and it's not easy to cover it in a lecture like this. I mean, each one of them requires a specific thing. The other things are there, and it is written there, so I wouldn't go into details of it. So next slide, please. You see, you people are working in this area, so you must be knowing about the rover, the first rover which was sent to Mars. It is called the Curiosity rover, and it had a instrument called CAM, and the instrument which I want to talk about is it used laser, and one of the persons whom I had chance to meet in 1977. His name is Chris Webster. He is one of the leading scientists in NASA Jet Propulsion Laboratory. So at the time I met him, he was in Bristol University in 1977 working for his PhD, and he was working on a technique called photoacoustic spectroscopy. So he was very kind to explain to me how the photoacoustic spectroscopy is applied, and it is detection of light by microphone. And it was such a technique that he has made his own microphone and he was detecting it. And from getting some data and information, I came back, and our mechanic was so good that he made a microphone with with the polythene films, which was coated with metal on one side, and we started photoacoustic spectroscopy in a small way. So that is my point of contact. But this person is very famous, and he has worked on the atmosphere of Mars, and the instrument which was loaded on that Curiosity rover, it has basically two important features. One was to study molecules, and the other was to study atoms. Now, for studying atoms, there is a technique called laser-induced breakdown spectroscopy. That is, it was a very powerful laser at the mast. So this is a vehicle, rover is a vehicle, and at the top there is a laser which can be pulse laser, which can be focused onto a rock, which is at a distance of about 7 or 8 meters, and it produces a spark. Now, the light which comes from the spark is received by a telescope, and it goes into the inside the spectrograph, and then it records the atomic emission in that spark. And this technique has been perfected in the laboratories, and it was for the first time that laser spectroscopy was used on a different planet other than Earth. And as Professor R.P. Singh indicated in his inaugural talk, the Perseverance rover, which has been sent in 2020, uses Raman spectroscopy for the first time on Mars. So these are highly technical things, and I do not have the capacity to describe to you in detail what it is. But what I would suggest you is that this Chris Webster has written two very important articles in Science. There is a famous journal called Science, and he has written two articles. One is 2013, the data based on Curiosity rover, and the other on other in 2000. Let me see which year it is. It is later. I think is it 2018. Yes, the other is 2018. Now, the paper that is 2013 deals with the isotopic abundance of carbon, hydrogen, oxygen. That is carbon 13 versus carbon 12, deuterium versus hydrogen, and oxygen 18 versus oxygen 16. So what they do is that this rover is very interesting. It can take out material from just like your in UP now there is this bulldozer thing. So there is an arm which can crack the rock and take a small sample and keep it inside, and then there is a lab which is called SAM, sample analysis lab or something. It crushes it and then it heats it. So the gases evolve out of it, and then they take infrared spectrum of these gases, and from these infrared spectrum, they detect the presence of isotopic molecules. Now, what it does is, it gives the idea of what is the rate of evaporation from the surface of Mars. Because what happens is that the heavier isotopes remain in the surface of Mars, and the lighter ones evaporate when light falls on it. So when you take the rock and crush it from the surface, and then you find that the abundance of heavier atoms, heavier isotope is more than that of the lighter one. So this gives about the history of history of rocks, and because the idea was to see if there was ever life on Mars, and they were looking for biological molecules, organic molecules. So this also gives the infrared spectroscopy also gives information about organic molecules. Now, in this this was just by the way. So this one, this instrument which can be put on a for detection of atmosphere is it uses a Cassegrain telescope, and so you can see the laser light which goes towards the atmosphere, and the scattered light from there is captured by the telescope, and then it is processed, and the spectrum is shown here. So you see, our Earth atmosphere is very dense; it has all kinds of things, and so it is very very complicated. So you see, there are many lines. I wouldn't go into detail, but what is important is that they have detected SO2. So there are these two lines which has been detected. So on the left-hand side, this broad peak that you see is because of SO2 molecule, and the other broad peak that you see on the right-hand panel is because of kerosene molecules. So from wherever they have studied the atmosphere, this is kind of pollution study, because SO2 is a polluting gas, and it gives acid rain and so on. And the kerosene is also pollution. So this is just an example how it is done. So next slide, please. So you see, this is an example of what Professor R.P. Singh was saying. On a satellite, you have this laser and also the detector system, and then you can sample the surface, or you can surface the molecule. And this is a beautiful spectrum from the atmosphere of Mars. And you see, this this spectrum is of CO2 molecule. It is the symmetric stretching vibration of CO2 molecule, and what you see as peaks are the rotational lines of these molecules. Now, you know, I'm sure many of you are not spectroscopists, but we have done with this. So a band has this band has three branches, three rotational branches. The sharp peak that you see is called Q branch. The one on the right-hand side is called P branch, and the one on the left-hand side, which is higher frequency, is called R branch. So R branch, Q branch, and P branch. Now, in Raman spectroscopy, in Raman imaging, you don't see take everything. You take the brightest thing. So if you have to make a Raman imaging of CO2 somewhere, then you would look for the peak which corresponds to the wavelength of this Q branch, and then you will use this in imaging the CO2 molecule. So I think this is all, and I will close my talk. I'm very sorry, perhaps I have exceeded my time, and thank you very much for my patience. I must tell you, I was very uncomfortable speaking to this chair, not seeing any of you, but I hope I have been able to convey some idea to you. Thank you very much.
Or in the chat box also you can type. Sir, there are few questions.
Okay, yes.
One question is there: is Raman spectroscopy used in satellite communication?
No, I don't think so. No, it is, you know, it is used for analysis of materials. In communication, I don't think it is. I don't know. But there are other simpler things and more efficient to use in communication.
How does the second question is there, sir? How does the polarizability of molecules change due to interaction of incident light? And why
Well,
is there just a ratio of...
Yes. You see, the incident light has a varying electric field. the electric field changes. So I showed you the example by two plates in which the polarity was changing, and when the polarity was changing, the electronic charge cloud was elongated on one side and then on the other side, and with the electric field variation in an electromagnetic beam, this will be periodic and therefore it will generate light of that frequency.
And sir, why there is just a ratio 1:10⁻⁷, the Raman effect is observed?
Well, this is to see how weak Raman effect is. I mean, this process is extremely weak. So only 1 out of a million photons produce Raman line. This is because of the intrinsic weakness of this process.
Thank you, sir. Thank you for the valuable talk, sir.
Thank you, Dr. Kumar. You have been very nice and helpful. So can I watch the others also, the other talk?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Very good.
Now we are going to have another talk, next talk by Dr. Ranjan Kumar Singh, professor in BHU. So he has very wide experience in Raman spectroscopy. So we are going to have a talk on fundamentals of Raman spectroscopy by Dr. Ranjan Kumar Singh.
So thank you very much to the organizers of the conference, Director IIRS and Dr. Sasi, for inviting me to give this talk. So my talk has to concentrate on basics of Raman spectroscopy. And just before me, we heard a good talk, very good, good talk from my excellent teacher, Professor S.N. Thakur, and continuing this journey. So let us start with a brief history of Raman. So Raman did BA in 1994. That time it was BA and MA 1996. While studying in MA, that he published his first paper. And at that time, it was necessary to have a broad experience to become a teacher or in scientific to select a scientific career. So Raman could not do that. Then he joined financial service in Calcutta in 1907. From 1907 to 1917, he continued his scientific interest and published 30 original articles, around 30 original articles, and that were in acoustics and vibrations. And actually, these papers recognized him as an international scientist, and he was appointed fellow of Royal Society in 1924. And of course, he discovered in 1928 the Raman effect, and later on awarded Nobel Prize in 1930. We every year celebrate 28th February as our National Science Day. So we feel proud that this is the Nobel Prize done for the work done on the Indian soil by an Indian scientist. So now let us understand how we can define Raman scattering. Raman scattering, if a monochromatic radiation of frequency h nu 0 is incident on a molecular system, the scattered part of radiation contains three types. One, reduced frequency, another one of same frequency, and another third one is the increased frequency. So the the photons which are scattered with reduced frequency, they are called Stokes photons, and accordingly the Stokes-Raman scattering. The photons which are scattered with the same frequency as that of the incident ones, this is called Rayleigh scattering, and the photons that are scattered with increased frequency, they are called anti-Stokes Raman scattering or anti-Stokes photons. So classically, this was experimental observation. Scientists tried to understand it theoretically. Then with the classical approach, what it could be explained that, okay, in a scattering process, reduced frequency and increased frequency can be observed. But the intensity could not be explained. Means intensity of Stokes and anti-Stokes scattering could not be explained. This can be understood with a energy level diagram. Let us hide na. So okay, this the lowest level is V0. This is ground vibrational level. V1 is the first excited vibrational level of ground electronic state. So according to Boltzmann's law, maximum number of molecules will be in V0 state. Small fraction around 10% to 5% will be in V1 state depending on the temperature of the sample. So when the incident light of frequency h nu 0 interacts with a molecule which is in V0 state, that will be promoted to a virtual state, and through virtual state it ends up at V1 state. And in this process you see the annihilated light has frequency h nu 0, but the created light has frequency h nu 0 minus delta E. Delta E is the energy difference between levels V1 and V2. So this is Stokes scattering. And if the molecule from the ground state is again comes to the ground state, the emitted frequency is same. This is Rayleigh scattering. And if the incident photon interacts with the molecule in the V1 state, it can come through virtual state to V0 state, and this one is anti-Stokes Raman scattering. Now V0 state has more population and V1 has less in population. So Stokes scattering, which is taking place from the molecules of V0 state, that will be more intense than the anti-Stokes scattering. In practice, in experiments, because the transition, you can see that this transition is from B0 to 1. This is from 1 to 0. The transition involved the same vibrational states. Therefore, almost same kind of information we can get from the anti-Stokes part of Raman scattering and the Stokes part of Raman scattering. So we can either experimentally record both sides, or we can record one side. So in material analysis, one side recording of the one side spectrum is good enough, and we can analyze them and get information about the material. But when we go to the space or interstellar media, then recording both sides, anti-Stokes as well as Stokes, will be more beneficial, which we can see just now. We see the intensity of Stokes is always higher than the anti-Stokes, and the Rayleigh line is so strong that that we need to exclude it from the experimental measurement. This is done by by inserting two parts. One is called nose filters and another one is called edge filter. When we use nose filter, then only the Rayleigh line is cut, and we can get both anti-Stokes and Stokes part. When we use edge filter, then we can cut the Rayleigh line as well as all anti-Stokes part, and we can get only Stokes Raman part. So in material analysis, it is sufficient to record only Stokes part. Okay, when we compute the intensity ratio of Stokes and anti-Stokes lines, then we find intensity of anti-Stokes line by the intensity of a Stokes line is nu0 plus nu vibrational to the power 4. This is mistake. And nu0 minus nu vibrational to the power 4. E to the power minus delta E by kT. You see, in this equation, this can be calculated experimentally. This is known, nu0, nu vibrational is known, and then we can calculate very accurately the ambient temperature of the sample. We can calculate the temperature of the sample. If we can get both anti-Stokes and the Stokes part of any material, we can calculate the temperature of that material. For example, if we send small Raman spectrometer to any space mission, and we can get this Stokes and anti-Stokes part, then we can calculate the temperature of that material or that region. Now, next one is the selection rule. This is very important. This is Raman scattering is a very weak process, as Professor S.N. Thakur also explained it, that 1 out of the 10 to the power 6, 1 out of 1 million incident photon is expected to be Raman scattered in best possible Raman scatterers, not in ordinary. So this one is why it is so low, because that can be understood with the scattering cross section. This is quantum mechanical phenomena, and the scattering cross section is like there is very less possibility, less probability of the Raman scattering. So selection rule is the set of is the condition which can say that, okay, this transition is allowed and this transition is not allowed. So Raman scattering is related with the vibrational transition. So during a vibration, if the polarizability changes, that molecule, that vibration is Raman active. And this polarizability change delta alpha by delta Q, the Raman intensity is proportional to delta alpha by delta Q square. So this change is sufficient to be observed experimentally. The time process, this is a scattering process. This is not absorption process and emission process. The matter is of time scale. The time scale of this Raman process is femtosecond, let us say 10 femtosecond. And to compare it with the fluorescence emission, you can see that fluorescence emission takes place in 10 to the power minus 8 second, or you can say in nanosecond time scale, and this Raman scattering process in femtosecond time scale. Okay. Now this is famous, well-known spectrum, and Raman spectrum. We are here to talk about Raman spectrum. So this Raman spectrum is involve transitions between rotational level. It involve transition between vibrational level, and the electromagnetic photons that are involved in rotational transitions falls in microwave region, and in vibrational level they fall in infrared region. So this rotational as well as vibrational transitions, Raman spectroscopy is useful. Okay, so for any molecule, there are 3n-5 for linear molecule and 3n-6 for non-linear molecule modes. For example, for CO2 molecule, there are 4 normal modes of vibrations, and for H2O molecule, there are 3 normal modes of vibration. For a smaller molecule, it is vibrations can be very easily pictorially depicted, but for larger, bigger molecules, it is a bit difficult, and we have to use some softwares. But we can understand with smaller molecules. For CO2 molecules, 3n-5 means 4 modes of vibration. So out of 4 modes of vibration, only those vibrations will be Raman active for which there is a change of polarizability during vibration. And the vibrations which are IR active, there is a change in dipole moment during vibrations. So for every these vibrational transitions can be one more important thing for interstellar system. This rotational Raman spectrum is also very useful, because in condensed phases the rotational structures are not seen, only vibrational structures are seen. But in gaseous phase, the rotational Raman spectrum is also useful. Okay, the infrared region can be divided into 3 regions: near, mid, and far infrared. Near means close to the visible region, far means far to the visible region. So the far IR region typically involve rotational transitions, mid IR usually involve stretching and bending vibrations, and near IR involve overtone bands. Overtone bands means delta V is equal to +-2, +-3, etc. These are generally observed in infrared spectra, not in Raman spectra. Overtones are generally observed only in infrared spectra. So Raman scattering is a very weak process, and we have to record the Raman spectra from any material. So it is better to know on what factors the intensity of the Raman line depends. So the first one is the target area. This is the scientific word. This we can call it cross section area. Raman scattering cross section. That is sigma new excitation. This is Raman scattering cross section, and this incident frequency nu to the power 4 and incident beam irradiance E0 and number of molecules in the particular state, and this is Boltzmann factor. So out of these factors, you see what are the factors which an experimenter can control. Then we can optimize the intensity and we can get the Raman spectrum. The scattering cross section we cannot control. The excitation frequency we can control. We can change the laser frequency. You see, it depends on fourth power of the laser frequency. So if we get IR excitation, then we have less Raman scattered intensity. And if we take blue or ultra UV radiation, UV laser, the scattered Raman intensity will be more. So we can select we can select the frequency of the incident laser beam, and accordingly we can change the intensity of the Raman line. So in number density, if the number of molecule in a state is more, so or the number of molecules is more, then we have concentration is more, then we have more intensity. And we can, from Boltzmann factor, we can see if the temperature is low, then intensity is more. So these are the factors. Basically, an experimenter can control the one thing, the incident, the frequency of the excitation source. So this is a relative scattering cross section of many processes. Absorption process, UV visible absorption, the scattering cross section is 10 to the power minus 8. IR absorption 10 to the power minus 21. Fluorescent 10 to the power minus 19. Relay 10 to the power minus 26. And you see the Raman 10 to the power minus 29. Resonance Raman 10 to the power minus 24. SIRS 10 to the power minus 15, and 10 to the power minus 16. So here we can have the idea that this Raman scattering has the lowest scattering cross section, 10 to the power minus 19. So in a spontaneous Raman scattering, we can control some of the factors and increase the Raman scattering. And there are other mechanisms through which we can increase the Raman scattering process, and we observe the Raman lines. For example, this is resonance Raman scattering. Raman scattering, and we will see in when the excitation frequency matches with the excited electronic state, then resonance occurs and the Raman scattering cross section increases. Surface enhanced Raman scattering, we will also see in the next slides, then when the molecule is adsorbed on a nanomaterial, then also the the Raman scattering cross section increases. So if we want to have an idea about the selection of laser line, so you can see that if we use 532 nanometer laser line, and we record the same spectrum, same band, 666 of CHCl3, then this one is 0.66, then with ultraviolet it is 13. So as we decrease the wavelength or increase the frequency, the intensity of the Raman line increases. Okay, if we get some Raman spectrum, we want to interpret it. What is the meaning of that Raman spectrum? Then there are certain standards which we can use. If the line is from 3200 between 3500, they can be of OH stretching, NH stretching, or CCH stretching. There are other characteristics also. This OH stretching is broad, and this NH stretching can be broad, can be sharp, and C triple bond C stretching is sharp. In 3000 we get CCH stretching. So these are the standards which we can use to understand our experimental results, and these are easily available. Wide range of these standards are available. Now we come to the next part. If we record any spectrum, Raman spectrum, or any other spectroscopic spectrum, then we get such kind of line only. The whole information is contained in this line only. Then we have to define certain parameters which can be connected with the physical properties of the material, and then we can have idea about the physical properties. So for any Raman line, we can define three parameters. One is integrated intensity, one is peak position nu zero, another one full width at half maximum FWHM. Another one can be integrated intensity or peak intensity. Anything we can use according to our problem. So now if we know nu zero, peak position, on which factors peak position depends? I don't have okay slide for this. On which factors peak position depend? For this we can just see the spring mass system, and the frequency of the spring mass system is given as nu is equal to 1/2 pi root under k by mu. K is the force constant and m is mass, and in two body problem it is reduced mass. So k by m, K is the force constant. So in the molecule, on which factors force constant depends? Who is providing the force constant stiffness to the vibration? So that is the electromagnetic force is present, and if there is any change in the charge distribution over the molecule, of course the molecule will remain neutral, but if there is intramolecular charge distribution, then this force constant will change, and accordingly the frequency will change. So this nu zero peak position is a static property of the material, and it changes according to the electromagnetic properties of the molecule and reduced mass of the molecule. The line width is a dynamic process. The line width we can understand from the uncertainty principle that every line, either rotational, vibrational, or electronic, every line has a width because delta E, delta T is a constant. So if the lifetime of a label is low, then energy uncertainty is more. That the line will be broader. Okay. Now बात कर लो, बता देना कि अभी आधा घंटा. So this is dynamical property. For example, if you think if we can think of a situation when a molecule is emitting or absorbing. Emitting molecule collides with some another other molecule, then what will happen? The emission process may be easier and it will take less time, and accordingly there will be a broadening. So this lifetime, the FWHM can be connected with the dynamical property of the material. If material is more, the intensity will be more. Then this integrated intensity can be connected with the concentration of the material. So these are the factors, and depending on the problem, other factors can also be decided. For example, if in interstellar spectra, if we get many overlapped lines and we want to have some dynamical information about the material, then we can define intensity as 3/4 maximum, because there will be less overlap in that region. So these parameters can be defined according to the problem. So some characteristics of the Raman line, and that characteristics can be used to have an idea about the material. The Raman spectra are, when the Raman spectra are obtained from the linearly polarized radiation, then scattered Raman line is polarized depending on the active vibration, and this is defined as depolarization ratio, and it can be useful to understand which vibration, or in turn to which molecule it belongs. So depolarization ratio can be calculated experimentally in liquids. It is very easily calculated if you put one polarizer in the incident beam and you put another analyzer in the Raman scattered beam. If you keep both the analyzer and polarizer parallel, this is parallel, and if you keep them perpendicular, then we get perpendicular component. And the ratio of perpendicular component to parallel component is depolarization ratio. We can see how it looks experimentally. You see, this one is the CCl4 spectrum, and when the two analyzer and polarizer are parallel, we get 3 peaks. 3 peaks, 1, 2, 3. When the analyzer and polarizer are perpendicular, we get 3 peaks, only 2 peaks. When the analyzer and polarizer are perpendicular, we get only 2 peaks. So this band is completely finished. This kind of Raman band is called depolarized Raman band, and polarized Raman band, and these two are depolarized Raman band. So if we have idea about the polarization, we can have some idea about the vibration. For CCl4, this is the symmetric stretching, CCl stretching. Okay, another important thing is that if there is a Raman spectrometer, we want to get Raman spectra or any other spectrometer, there is a slit through which the signal enters. So how much we keep the slit, this is also very important, especially in Raman. You see, you see this one is the Raman spectra of two bands, one 999 and 1024 of chlorobenzene, only at 6 slit openings. Only the slit entrance slit width has been changed, nothing else. The lowest one is of 50 micron and the uppermost is 300 micron. If you see, the lowest one, which is recorded at 50 micron slit opening, has the Raman bands are very sharp. But at 300 micron, the Raman bands are much wider. So nothing has changed, only slit width has changed and the band has broadened. If this broadening is more, then we have to take care of it. Otherwise, we cannot get precise information about the material. Next, we see another example of that. This one is the 50 micron. This is the laser line, very sharp line. This one is small. And at 300, 400 micron, you see this is so broad. Even the shape of the line has changed. So from these two graphs, we can see that if the intrinsic Raman line is sharper, then the effect of slit is more important. So if according to an estimate, if the intrinsic Raman line width is of the same order at that of the slit contribution, then we need to get rid of the slit contribution. And this can be done with this simple formula, and x square x cube, where x is S slit function. Slit function means a very sharp line, laser line or plasma line recorded at the same slit opening, and we can use this formula and we can get rid of this slit opening. So I want to emphasize at this slide that if the intrinsic width of the Raman line is very sharp, then we have to be very careful how much slit we are opening. And if we are opening more slit, then we have to exclude the effect of the slit, and that can be excluded in many ways. First, we want to just FW. If we want to extract the true FWHM, we can use this formula. If you want to extract the entire profile, then we can go for Fourier transform for individual bands. Okay, so spontaneous Raman scattering is used in many cases. We have been using it in hydrogen bonds. It is a label free. You don't need some external standards. 2D material and nanomaterials, it is being used. It is used in chemically spectral imaging, drug delivery. There are many uses. You cannot name a single branch of science or technology where Raman spectroscopy is not being used. So Raman spectroscopy, the we have been discussing. Professor S.N. Thakur also told that the Raman scattering cross section is low, and in fact it is a very big problem that how to get the Raman spectra. And because of that reason, till the advent of laser, the Raman spectroscopy was kept kept behind many other techniques. And after the advent of laser, when the high intense exciting sources were available, the Raman spectroscopy came in, and different branches of different variants of Raman spectroscopy were discovered. So in this spectrum, in order to increase the Raman intensity of the Raman band, people tried resonance Raman scattering. In spontaneous Raman scattering, you see, we always try to select a laser line which is far below the first excited electronic state. Because once you are inside the electronic state, the fluorescence comes in, and that will mask the Raman spectra, because fluorescence emission is very efficient. So if this exciting frequency is close to the first excited electronic state, we are in pre-resonance Raman scattering, and we see in certain cases some amount of enhancement. And if we are inside the excited electronic state, it and the laser matches with some of the vibrational state, this is discrete resonance scattering. And if we are in the continuum of the excited electronic state, this is a pure resonance Raman scattering. So in resonance, in biological system, resonance Raman scattering has been widely used. We select a laser line which matches with the excited electronic state. Means in the virtual level is now in the excited electronic state, and we get some enhancement. For spontaneous Raman scattering, people also using surface enhanced Raman scattering. This is also a experimental technique to increase the Raman scattering part. You see now. So in surface enhanced Raman scattering, in short we call it SIRS. In SIRS, what we do, the analyte material is adsorbed on a nanomaterial. Nanomaterial can be anyone, metal, AG, AU, or people are trying many semiconducting materials or core cell materials. So nanomaterials, the analytes are adsorbed on the nanomaterial. And you see one example that normal in this is lower one is the normal Raman spectra. We did not see any band clearly, but when the same material is adsorbed on a nanomaterial, then we get very sharp Raman bands. So in nanomaterials, what happens? In nanomaterial, there are two types of enhancement. One is chemical enhancement, another one is electromagnetic enhancement. In electromagnetic enhancement, what happens that the surface plasmons, there is a surface plasmon frequency in nanomaterial, and if this plasmon frequency matches with the scattered radiation, then the intensity increases. And another phenomena is chemical enhancement, in which the homolumo level are the modified, Fermi level are modified. So without going into detail of this mechanism, let us see applications. There are many applications of SIRS, and of course biological applications. And if we are able to increase the intensity of the Raman line, so what is the time now? 12:20. Okay. So now I I want to come to the instrumentation part of the Raman spectrometer. So for any Raman spectrometer, just this is a template. The exciting source, this is a laser, and lasers we can select according to our requirement. The wavelength of the laser we can select. So commonly used laser are helium, cadmium, argon ion laser. This gives a high power argon ion laser gives 10 lines, but the low power also gives 2 lines. Helium neon, diode lasers, ND-YAG laser. So these are the common lasers. We can use any frequency, and of course the optics of the spectrometer should also be compatible with the exciting laser. Sample after the scattered radiation is detected with a spectrometer. That a spectrometer contains many part. We will see. Oh, misplaced. Oh, a spectrometer misplaced. A spectrometer. I come independent. Okay. So I am sorry. I open a different one. Okay. So is it visible? Is it visible, sir? कोई बोल नहीं रहा है.
Yes, sir.
Yes, 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 it is
Okay,
visible.
okay. Okay. So this is one optical ray diagram for a Raman spectrometer. So you see there is a laser, tunable laser, and we can select one frequency. Let us say this is a krypton ion laser or argon ion laser. So these lasers on many frequencies, one frequency can be selected with a prism, and by rotating a prism, any of the desired frequency can be selected. And that frequency, there is, if this is a gas laser, then there is always associated plasma lines with the gas lasers. And if you don't remove the plasma lines from the gas laser, then they will also appear in the Raman spectrum, and we will be confused with the Raman spectrum. So whenever we are using gas lasers, it is necessary that plasma lines have to be removed. So there is a assembly that removes plasma lines, and this is called plasma line filter. So the gas laser, or for solid state laser, it is not necessary. So the laser after removing the plasma line enters into a microscope. Microscope, why? In earlier days, microscope was not being used, but we were trying different kind of optics to collect the maximum amount of the scattered signal. But this was but now the microscope is coupled with the Raman spectrometer, which can collect the maximum amount of the Raman scattered signal. So the laser line through the microscope comes to the comes on the sample, and the scattered part is collected with the same microscope, and you see this enters through this slit into the spectrometer, and from a mirror reflected to one grating. The grating disperse Now different wavelengths travel at slightly different angle, and again they are reflected, they pass through another slit, and after reflection it again two gratings. So two grating dispersion is more. So after two grating they enters into the CCD. CCD in earlier days, PMT, photomultiplier tube we are used, and in photomultiplier tube 1 by 1 wavelength was covered, but in CCD maximum wavelength is covered in one snap like a photograph. So CCD, and that CCD is connected with a computer. Actually the whole system, everything is synchronized, and with one command the whole system moved in a synchronized way, and we get the Raman spectrum. This is a typical diagram from a standard company Jovin Yuan, JY we say. And if we come to this Renishaw model, then they have a different template, and you see the laser line is coming with the beam, laser beam is coming, and laser beam is beam shaped. Beam shaped means the laser line is coming very sharp, that has the diameter of the beam has to be increased. So diameter is increased, and because the extended beam can be focused on a smaller area with the microscope, so beam is expanded, and this beam enters into the microscope on the sample, and it is again collected and go to the grating through a triangular mirror and collected with the CCD, and we get the Raman spectrum. Again the same thing we have done it. Okay, actually it is so one part, how much time left? I think
Sir, please finish as soon as possible, sir.
okay, because
Yeah.
I thought I should ask. Okay, so basic part I have finished, and now I just take one example, and one example of hydrogen bond, which can be understood very easily. So this, you see, hydrogen bonds had very good signature of in the Raman spectrum. So this can be also useful for your interstellar material, because the molecules are hydrogen bonded at many places. The signatures of hydrogen bond is very precise in this case. So you see, this one is the neat acetonitrile. There are two bands. One is this corresponds to, there are two bands, deconvoluted spectra are shown here. One band corresponds to self-associated, and one is neat acetonitrile. If we mix it with methanol, then you see the two bands remains, but a third band also appears. That is because of the hydrogen bonded complex of the Raman of the acetonitrile with methanol. And you see this band is reduced, means this self-associated acetonitrile, the two acetonitrile molecules which are connected through hydrogen bond, they break, and some of them make hydrogen bond with methanol molecule. So I end up here, and if you ask some questions, then I will be happy to answer.
Participants are requested to ask the questions.
Sure.
Or you can write in the chat also.
Can you increase the sigma by?
can you increase sigma by condensing the material?
No. By condensing the material, we can increase the concentration of the scatterers and the intensity will increase. Of course, intensity will increase, but not because of increasing sigma. It is because of more number of scattered photons will be there.
Oh, another question. Raman spectra has to perform in dark room, so how can it use for atmospheric molecule detection?
Okay, then it is performed in dark room because we are using visible lasers. Because we are using, using visible lasers, then the visible light from tube light and bulbs, they can interfere with the Raman spectra because the region is same. But if we are using UV light or if we are using IR light, then that will not interfere. That can be used. We can do the Raman measurement with UV light in light also, or with IR light. This light will affect less.
There are two more questions.
Yeah.
For a common person, what is the difference between the Raman effect and how it differs from Rayleigh scattering?
Okay. Rayleigh scattering, in both the processes there is scattering from the molecule, and for common person, of course the frequency is changed, wavelength is changed, the color will change.
And one more question. Why we remove the plasma line in gas laser, sir?
Okay, because the plasma line has also the frequency that is around the Raman bands. So when we record the Raman spectra of any material with a gas laser and plasma lines are not removed, then those plasma lines will also come at those positions, and that they also look like they are more sharp, a bit sharper. They also interfere, they also come on the Raman spectrum. So sometimes it will be difficult to decide whether it is plasma line or it is Raman band.
Thank you for your informative talk on fundamentals of Raman spectroscopy. We are very much thankful to Dr. Ranjan Kumar Singh for his valuable and informative talk. And now I am going to invite the next talk by Dr. Mamta Chauhan that will be related to the geological application. So, Dr. Mamta, please share your screen.
Okay, sir, I'm sharing my screen.
And sir, S.N. Thakur, sir. Lunch break, and after that again we will be here at 2:30 for the next talk. So after the talk of Dr. Mamta Chauhan, there will be break, and again we will continue the session at 2:30 afternoon. So Dr. Mamta, please continue your talk.
So, namaskar and good afternoon to all. As the earlier lectures by Professor S.N. Thakur sir and Professor R.K. Singh have very well explained the history, fundamental principles, working and applications of Raman spectroscopy and with application in biological medical sciences. So I will highlight on the applications of Raman's spectroscopy for earth and planetary sciences, especially focusing on the geological aspects. So let me start. So as the earlier lecture have very well explained all these basic fundamental, I just highlight the importance of the Raman spectroscopy for geological application. the main advantage, the Raman spectroscopy in mineralogy is mainly utilized to identify minerals, rocks, and detect associated organic compounds. And the key advantages are it is non-destructive. That means it preserves samples integrity, and minimum sample preparation is required. So it is very suitable for in situ measurement, and it is sensitive to changes in molecular polarizability during molecular vibration and ability to analyze solid, liquid, and gases. So the position, intensity, and width of diagnostic peaks of resulting Raman spectra depend on crystal orientation, grain size, crystallinity, grain size, chemistry of rock mineral, can be used for performing qualitative and quantitative analysis of rocks and minerals for geological applications. Now, just to brief about the difference between Raman and IIR spectroscopy, because both are very well-known analytical techniques that are utilized in geologic applications. Both probes molecular vibrations. So, but the Raman spectroscopy utilizes the visible portion, some part of ultraviolet regions and part of near infrared regions, whereas IIR spectrum mainly utilizes the whole of the IIR spectrum. And IIR spectrum results from absorption of light by vibrating molecules, and the absorption is essentially estimated in the same direction as the incident beam, while the Raman spectrum results from the scattering of light in vibrating molecules, and it is measured in the right angles to the incident beams. And other important differences, Raman spectroscopy is sensitive to change in polarizability of the molecules, as already highlighted in the earlier lectures. IIR spectroscopy is sensitive to change in dipole moments. And the factor that which tend to increase the complexity in IIR spectra is the overtone and combination bands, which may be quite strong while they are rarely seen in Raman spectroscopy. So main advantage of Raman spectroscopy is simplicity of spectra, capability to analyze solid, liquid, and gases, whereas IIR spectroscopy cannot be utilized, or it is less utilized for liquid samples. And Raman spectroscopy is sensitive to homonuclear molecular bonds, whereas in this IIR spectroscopy is responsive with regard to heteronuclear functional group vibrations and polar bonds, and there is no sample preparation requirement. So that makes Raman spectroscopy a suitable technique for space exploration. Now coming to the applications of Earth and planetary sciences. Raman spectroscopy provide physical chemical information about the composition of material being analyzed. It reveals unique information related with the chemical composition, crystal structure, dynamics of crystalline and anamorphous state. So whether the mineral is the material is in crystalline state or whether it is in amorphous state can be readily detected. So it is used for qualitative as well as quantitative phase identification and characterization by conducting individual point analysis, one-dimensional line scans, and or even three-dimensional hyperspectral map. So it has immense use in mineral identification and characterization, for geochemistry and petrology, for exploration of new minerals, to understand surface and subsurface processes, and for planetary surface analysis, and also in geobiology and astrobiology. All these important aspects I will be covering in the succeeding slides. So for the mineralogy, in mineralogy, to identify the minerals, which are common rock forming minerals, and there's various types of the rocks of the earth, distinguish between various polymorphs and the solid solutions, determine the shock history of the minerals in impact rocks. So all the important minerals almost all the rocks and minerals can be identified using Raman spectroscopy. And there is a complete database of rocks and minerals in the from the American Mineralogical database that has characterized all the important rock forming minerals, silicates, carbonates, sulfates, all of the minerals are there in the solid solutions. Along with the Raman spectra have been provided along with in the XRD analysis. So these are examples of some of the Raman spectra of the some of the common rock forming mineral. For example, this is the spectra of forsterite mineral, the olivine. This is the spectra of the epidote mineral, which is a sorosilicate. Similarly, it is one cyclosilicates and the Raman spectra. These are all taken from. This is the source of the paper from which I have taken this spectra, but all the spectra they are available. I mean, they have been derived from the RUFF spectral library that is available online. So the spectra for the muscovite, phyllosilicates, muscovite, for the tectosilicates, quartz, and these sulfates. These are some of the examples where the Raman spectra, that's in intensity versus Raman shift, is showing, and with the peaks showing the characteristic absorption of the that intensity peaks for the mineral being analyzed. And besides in mineralogy, it is not only identified but also to characterize and differentiate minerals on the basis of functional group related with the mineral structures. So, for example, this is the example of taken for the calcite and dolomite. Both of them are characterized by the chemical composition is CaMg, CO carbonate minerals. So, in these carbonate minerals, the calcite and dolomite, they are mainly characterized by 4 prominent vibration modes because of symmetrical and asymmetrical stretching and deformation that are prevalent at 4 important points: 1440 per centimeter, 1088, 715, and 278. So, for the calcite, these important prominent vibrational modes are mainly at 1361, 1047, 750, and 157. So, while these the vibrational mode for the carbonates, so in the calcite, that is calcium carbonate, they will be present at these particular peak positions. And whereas in the dolomite, these are the peak position 1393, 1098, 1069, and all this. So the difference in the calcium and magnesium carbonate, so although they belong to the same solid solutions, the difference arises due to difference in the structural variations. As you know, that calcite is crystallizes in trigonal structure, whereas dolomite crystallizes in hexagonal structure. So the difference in the crystal structure results in the different shift in the peaks of the Raman vibration peaks, and that help in their identification as well as in differentiating the various phases. And this difference in the peak positions is also because of degree of cation substitution. For example, while when dolomite and calcite versus calcium carbonate, the substitution of magnesium for the calcium may result in, to different degree, may result in different position of the peaks. Similarly, for the identification and characterization of minerals, these are also used for the gemology, for gemstone identification, their characterization, whether these are natural or synthetic, and whether they has been undergone some treatment at high temperature and pressure conditions. So, in order to distinguish between whether it is a fake or it is an authentic one gemstones. So this is example I have taken for the tourmaline mineral, which is obtained from the same source, and it is showing more or less similar color. Although they belong to the tourmaline system, they are the different solid solutions. So it is fluoroiodiocoicite and this is fluoroabiatite. Tourmaline, I like to state that they are calcium, lithium, alumino-borosilicates. So the one of the phase, that is fluoroiodiocoicite, it is the calcium pairing, and the fluoroabiatite is the it is sodium bearing, and this one is the calcium bearing. So substitution of calcium and this soda may result in different the shift in the peak position. This is the Raman spectra for the fluoro LBA type, and this is the Raman spectra for fluoro EDA core sites. And you can see that this the shift in the peak position. So the Raman spectroscopy is very ideal in discriminating the various solid solution within a particular mineral systems. In petrology, it is used for characterizing mineral association in rock samples. So, as we know that rock is an aggregate of the mineral, so various mineral association can be characterized using Raman spectroscopy. Investigate phase transition in mineral at different temperature and at different temperature pressure conditions, and determination of the province, whether it is sedimentary or igneous, from where the mineral has been derived. This province can be determined, and to quantify stress and strain affecting the host mineral in close proximity with the inclusion. For example, this is example I have taken where the diamond, you can see this transmitted light image of a diamond, which is surrounding, this is the chromite inclusions present within the diamond crystals. And this is the Raman spectra of this magnesium chromite inclusions. And this is the Raman map of the this crystal inclusions in the diamonds. And here we can see the change in the color, and it is showing the strain halo. So the strain pattern in the this part of the particular inclusion of magnesium iron chromite in the diamond has been can be identified. So it has immense use in petrology. Similar example I have taken for the for the siderite mineral, that is iron carbonate, which is taken at 3 different pressures in diamond and will cell in the controlled experimental conditions, and their spectra was observed at different when they are subjected to different pressure conditions. Now, like you can see, the different colors are indicating the different pressure conditions, and you can see the whatever with the characteristic absorption peak was there, it is showing shifting. So high spin and low spin transition of iron can be identified, and these can be studied. So Raman has immense application in study of pressure-induced changes in which is reflected by the changes in the Raman shift, and to determine the present remnant pressure acting on inclusion within high pressure minerals. For example, this is the case I have taken. Reconstruction of primary formation conditions, and these techniques, this application can be used Raman-based pressure sensors with particular advantages compared with the pressure determination from the emission lines. For geochemistry, the Raman provide data on the solubility, redox state, that is oxidation reduction states, fluid melt partitioning, which are very crucial for hydrothermal geochemistry. This is the example I have taken. This is the example of the olivine inclusion within a diamond. So the both are characterized by both are these are all, diamond crystals by having olivine inclusions. But their sources are different. This is from the kimberlite pike of Yakuta in Russia, and this is part of the placer deposits. So and these are the Raman spectra of the olivines. And they have the olivine crystal. The olivine is characterized by a doublet, and these doublets, they are the most intense bands of stretching because of silica SiO4, which is observed at around 825 and 857. With the change in the pressure, they show a shifting in this. So this doublet can be used to determine residual pressure in the inclusions and evaluate the pressure of diamond crystallization. So the Raman spectroscopy can be utilized in understanding the various this types of means pressure related variation induced in a particular inclusions, and that can be tracked using Raman spectroscopy. For hydrothermal mineral exploration, it is very important tool for exploration of hydrothermal mineral, since specific alteration mineral assemblages may relate to significant ore forming processes. And so these hydrothermal alteration processes are characterized by formation of certain important minerals. These are the spectra of the various alteration minerals like pyrophyllite, muscovite, paragonite, chlorite. So these are the alteration minerals, and the characteristic spectra in this spectral in the Raman. This is the Raman spectra of this particular minerals, and so these minerals can be identified based on the spectral peaks, and they can be utilized to understand the geothermal process, or to explore, or to detect any ore forming process over there. In rare earth studies, rare earths, as we know, that they are critical for modern technology and their demands are increasing worldwide. The principal sources of rare earths are carbonatite and carbonate-related supergene laterite deposits. The rare earth deposits commonly host rare earths and phosphate mineral, which is characterized by valuable amount of volatile components. So phosphate apatite is a phosphate mineral, and the different types of apatites like rhabdophene, monoxide, can be distinguished on the and characterized on the basis of the absorption peaks in the region 20 and 2800 to 3600, and that are indicative of the presence or absence of water. Since the identification of volatile compounds may present challenges in other analytical techniques like inductively coupled plasma mass spectroscopy and EPMA techniques. So this technique is very useful in detecting these types of phases and capturing the variability. This is the Raman spectra of the apatite from Mount Weld carbonatite. This is the Raman, the spectra of the apatite in the carbonatite, and this is the spectra of the apatite from the silicate. And you can see the differences and the subtle differences, presence of monzonite and other phases, and so they can be clearly distinguished and characterized and captured for the variability present. Now coming to the geobiology and astrobiology applications. Given the ability of the Raman spectroscopy to detect both inorganic mineral and organic species simultaneously and non-destructively, so Raman spectroscopy is an ideal technique to study organic mineral interrelationship, and such type of interaction or interrelationship could be metabolically induced between microbes and minerals, or by biomineralization process. Biomineralization process is the process where it is the formation of a geologically recognized mineral by biological process. That means the various organic mineral interaction by whether they are formed by metabolically induced, or whether they are by any geological process, they can be readily captured by Raman spectroscopies. And geobiologists, as we know, that are using Raman spectroscopy to characterize and identify biomolecules and attempt to answer such as when and under what condition life begin, and that is life formed, and how can we verify biogeneity in geological record, and understand what governs the relation between the living world and mineral world. So for answering these questions, study of extremophiles, that is the life that has that can survive in the extreme conditions, and the early life, the life that existed on the earth about 3.8 billion years ago, that needs to be characterized, and that can be compared with the extraterrestrial scenarios on the other planetary bodies like Mars, Titan, Enceladus, and Europe. So this is very important part of planned space missions undertaken to the planets and their satellites in search of extant or extant life signatures. Raman imaging has an advantage as it is able to map, among other features, shift in the mineral peak position, possibly associated with a change in chemistry. Another important point is it is very important to variation in the peak width due to changes or differences in the degree of crystallinity can be captured by Raman spectra, and the variation in ratio of different peak intensity due to change in the crystal orientation also can captured. So its capability to map differences in chemistry of mineral organics as well as their possible co-variation at sub-microscopic level make it as an ideal tool in geobiology and astrobiology. These are the examples I have taken from the literatures where these are the Fourier transform Raman spectrum taken with 1064 nanometer excitation laser in algal zone of endolithic community in Antarctica desert ecosystem. You can see the various phases like chlorophyll, carotenoid, and also the various pigments and the various in pigments and the other information provided by spectrum of calcium oxalate which provide the hydration state. So the spectra has captured beautifully the various phases present in this particular the algal zone. And this is the Raman spectra taken with the same algal zone taken with the deep UV excitation at 248.6 nanometer of a single stranded DNA molecules. And these are the Raman imaging for 4 experimental grown juvenile of the corals. This color represents yellow, one is for aragonite and the blue for the calcite. That is the different phases of carbonate, that is calcium carbonate in different crystal structures. So aragonite and calcite, which are very important for their or are observed in the coral communities. And this particular numbers 5.3, 2.7, 1. These indicate the magnesium calcium ratio of aqueous solution in which the coral begins. So you can see how beautifully the Raman spectroscopy can analyze and characterize the biomolecules. Now coming to the evidences of the life on Mars. Mars has been forefront of astronomical observation as we struggle to understand our place in universe. Ever since telescopic advancement and dawn of space age, it is clear that Mars has a cold and dry environment, devoid of life. As we continue to explore Mars from orbiter and rover, it is obvious that Mars has a very different past. All these observations, including NASA's Curiosity rover, indicate that Mars has period of stable liquid water on its surface and that habitable environmental condition existed during significant portions of the Martian history. The orbital and in situ observation provided evidences of volcanism and the various surfacial features in form of dryer lakes, delta deposits, outflow channels, interior layer deposits, or be it a detection of methane from the Mars and the direct evidences of the life water from the recurring slope lineae, which are the dark streaks present on the greater rim, where the water can be seen trickling. Has been detected by trickling, which indicates the presence of water in the subsurface in the form of ice. So all these indications from all these observations from in situ and orbital measurements, as well as the detection of clay minerals, carbonate, sulfate, halides, and sedimentary units. All these indicate presence of potential habitable environment during first billion years of Martian history. Current Martian surface is inhospitable place for most of the organic molecules due to high UV flux. However, organic material have been identified in Gale crater from Curiosity rover and Martian meteoroids in form of hydrocarbon components. So, considering these, to address these questions and understand potential habitability and look for evidences of past life, NASA has launched Perseverance rover to the Mars in 2020 that landed on the zero crater of the Mars in 2021. In planetary exploration, for the first time, Raman have been used, which is a this particular Perseverance rover was carrying 7 instruments. Among them, there was one robotic arm-mounted instrument on board Perseverance, which was Sherlock, scanning habitable environment with Raman and luminescence for organic and chemicals. And its main aim to acquire information about the mineralogy and crystalline structure of targeted rocks, detection of organic compounds, study the impact of ultraviolet radiation and spectroscopy of a reference organic molecule on the Mars surface. This Sherlock instrument combines fluorescence to detect fluorescence emission from organics in the spectral range of 274 to 370 nanometer, and along with it has Raman scattered also detect Raman scattered photons in the range of 250 to 273 nanometer regions. Both are required simultaneously for detection of organic molecules and identification of functional group of organics, chemicals, and minerals. Now, this is the zero crater. So the main aim of the this Perseverance rover, they were out of the 4 objectives. The 2 objectives were to explore astrobiologically relevant ancient environment on the Mars, to decipher its geological process and history, and including the assessment of past habitability, and assess the biosignature preservation potential within the selected geological environment, and search for potential biosignatures. So this is the landing site of the zero crater, the Mars Perseverance rover. It is the zero crater, which is about 45 kilometer diameter impact structure. It hosts open base lake during late Neogen and early Hesperian, that is early part of the Martian history. It is associated with the large carbonate deposits identified on the Mars. It has a well-preserved delta with clays and carbonate-bearing sediments, and which is well suited for preservation of all of the organics. And these are some of the spectra results published from the samples analyzed from the various formations of the zero craters. These are detected with both fluorescence and Raman spectra. The results of the organic material from the Ramans and fluorescence are co-located with the specific mineral observations. And the journal's partial correlation indicate that organic molecules have been abiotically deposited aqueously or synthesized within these altered volcanic material within crater floor. Difference in nature and distribution indicate that different aqueous alterations or deposition processes would have occurred, contributing to diversity. However, the confirmation of organic origin and specific identification of these molecules will require samples to be returned to the Earth for laboratory analysis. These organics were associated with low intensity 340 nanometer peak fluorescence, and they were widespread with no apparent association with any particular minerals. Organics associated with high intensity 40 nanometer correlated with the carbonate, phosphates, and amorphous silica. So these were some of the results obtained from the Sherlock Raman spectroscopy, and that has analyzed the zero craters geological formations. Now, European Space Agency send its second ExoMars missions. It is planning to send the first ExoMars missions was sent in 2016. It does at Trace Gas Orbiter. So it is planning a second ExoMars mission, which will deploy ExoMars rover called Rosalind Franklin. And this mission is planned in 2028. This is Europe's first Mars rover to look for the evidence of past life on the Mars and for characterizing past habitability of the Mars. There are 9 scientific instruments, and among them, one instrument is Raman laser spectrometer, and which will work in Martian environment. The range of the analysis will be 70 to 4,200 per centimeter, and working distance of 15 micrometers, spot analysis 15 micrometer, and spectral resolution of 6 to 10 per centimeter. This rover, Rosalind Franklin rover, is equipped with a drill that will dig at about 2 meters within the ground. And this is the landing site that has been selected for this ExoMars rover, Rosalind Franklin. And this is Oxium Planum. This is the Zero crater. This is the color-coded elevation map of the Mars, showing the various features. These are the depressed regions indicated by blue color, and these are the northern highland regions, and these are the elevated region characterized by volcanic features. So this in the equatorial region, this is the Zero crater location for the landing of the Curiosity rover, and this is the Oxia Planum region, which is planned for this ExoMars mission. This landing site is located within the Martian equator, and these are lowlands and plains, and that were once submerged in water and fed by a number of streams. This site is rich in clay, indicating that water was once played a significant role in these regions, and the age of the regions is around 3.6 billion years, and it has also undergone periods of volcanism, and that is indicated by the presence of basaltic flows over there. So Oxia Planum, given its geological history, is very significant locations to search for preserved chemical biomarkers and even microfossils, if there is any, dating back to billions of years. So this is a case study of various carbonates whereby Raman spectra has been gathered by using Raman, the Raman laser spectrolator simulator. And this is mainly the minerals are the carbonates, dolomite, and the various phases of carbonate, dolomite, calcite, anchorite, and aragonite. Now, it is yet another example to deploy a Raman in the planetary missions, and this is a Martian moon exploration mission. It is a robotic space probe which is developed by JAXA and will be launched in 2026. It will be the first mission to land on the Phobos, one of the moon of the Mars. Mars has actually 2 moons, Phobos and Deimos. So it is targeted to land on the Phobos surface, and it has 7 scientific instruments, and among them there is one Raman spectroscopic. RAX is also there that will do Raman spectroscopy. So this robotic space probe will bring back samples from the Phobos and conduct flyby operation for demos and monitor Mars climate. And this is its rover, Edifix rover. That is a French-German rover that will be deployed in the Martian Moon Exploration (MMX) mission. And this Edifix rover is about 25 kg, and it will weight only equivalent to 15 grams on Phobos surface. MMX these are some of the examples of the in situ surface exploration analysis that has been done prior to sending these missions. for characterizing the various minerals which are expected in the Martian environment or on the Phobos surface. These are the Raman spectra for clinopyroxene, olivine, plagioclase minerals, and the with Raman images of the various phases present. So this is all about that and how the Raman spectroscopy will be utilized in future Raman missions. Now coming to one of the study that we have undertaken for the Martian analog sites, Indian-based Martian analog sites, where we have selected some of the sites which are can be considered as which could preserve the signature of extant or extinct life that may be present or have an analogy with the Martian atmosphere or Martian surface. So these are some of the regions that has been selected. In the Ladakh region, thermal and hot springs were selected. And these are one of the regions in the Jhamar Kotra, which is where rock phosphate mines is there, and then there beautiful stromatolites, that is evidences of ancient life on the earth is preserved in form of rock phosphate. So these some of the regions we have selected in the Indian analog context, having analogy with the Martian's habitable conditions in order to understand how this signature how these minerals would have formed and how they preserve the habitable condition in extreme conditions. So these are the saline lake and hot spring where we expect extreme form of extreme form of life. So these are hot spring of the Chumthang, Puga, Kedar, Somurari. They have been captured. This is my initial part of the work that I have undertaken. So I have collected the samples, and beside analyzing for using other spectroscopy that may include this VNIR spectroscopy, FTIR spectroscopy, and other geochemical analysis, we are also attempting to analyze them for using Raman spectra. Since I have already explained, it's the beauty of Raman spectra that it can measure both organic as well as inorganic minerals. And so these are some of the spectra which were initially measured. Analysis were done. So these are the Raman spectra presented in intensity versus wavelength shift recorded over a range of 200 to 400 per centimeter. From the Martian analog sites, the Ladakh and this Puga Lake spectra, and this is the Raman spectra of the Jhamar Kotra phosphorite. And this spectroscopic analysis was conducted by excitation of sample using 532 nanometer laser with neutral density filter of 50%, and spectral range was scanned from 50 to 4000 per centimeter with 20 second acquisition time, acquisition and 4 time accumulation time. And these analysis were done at IIP Dehradun. So these and various other samples we have done, and we are in process of analyzing those samples. So this is the initial part of the study that we are conducting for Martian analogs sites on Indian in Indian context, and we are analyzing from them astrobiological aspects, whether how the signature of the organic molecules and extend life or in form of preserved fossils, or the life that is proliferating in extreme conditions, how the signature and what is the associated mineralogy over there that can be characterized, beautifully characterized by the Raman spectra. So we have undertaken this study. So to summarize, Raman is a very powerful, versatile tool for understanding Earth's geology, geochemistry, surface, subsurface, and environmental process, and it provides detailed molecular information that can aid in mineral identification, characterization, exploration, and insight into both our planet, our Earth, and other planet and planetary bodies in the solar system to study the geological and chemical process. So that's all from my side. These are the cited sources, because since I have started working means initial part of my work has started. So most of the examples or application I have taken from these uh, resources. So I have taken the example from all these publications. So that's all from my side. Thank you.
Thank you, Dr. Mamta Chauhan. Before going for the break, if there are some questions, then quickly we can take 1 to 2 questions from the participants, if they have. Yeah, there are questions. How is spectroscopy used to identify minerals and rocks in geological studies?
The Raman spectroscopy, I think they are highlighting the spectroscopy on the basis of the peaks, the dominant peaks. So for because we understand that there may be multiple peaks. So on the basis of the prominent peaks, and by then comparing it with the standard reference minerals that is present in the spectral library, we can identify the minerals and rocks using Raman spectroscopy.
And I think the second question is also visible to you. What role does spectroscopy?
What role does spectroscopy play in remote sensing for geological applications? Since I have already highlighted that Raman spectroscopy is very effective because sample preparation is not required and it is non-destructive. That means it preserves the sample entity and it can characterize both organic as well as inorganic minerals. From astrobiological aspect also, and also from the geological aspect also, that is very helpful. Then third question is, can spectroscopy help in determining the composition of soil? And yes, I have already stated that both the composition, the chemical composition of the soil, sediments, everything that can be analyzed. What are the different types of spectroscopy used in geology? How do they differ? The spectroscopy means they can be if they are in maybe like reflectance spectroscopy is there, infrared spectroscopy is there, and then I have told the difference between reflectance and infrared spectroscopy. While this reflectance spectroscopy, it is mainly based on the electronic transitions, while the IR spectroscopy and this Raman spectroscopy is based on vibration, molecular vibrations. So these are the various spectroscopy. Besides, there are other spectroscopy that are used for analytical techniques, X-ray, fluorescence, and that mass spectroscopy. And there are many types which are used in analysis and as well as for capturing the spectra. What is the difference? Okay. How does spectroscopy assist in analyzing the Earth, atmosphere, and surface for signs of geological process? By means observing or um, by analyzing or the characteristic spectra, which is showing the prominent absorption for any particular phase, that's how we can identify them. And then on the basis of a detailed analysis, we can understand means to which chemical composition or which particular mineral it has been formed or it belongs to. So it has mainly for identifying and characterization. So that can be used in earth and atmospheric surface. For also the processes I have already that for various means variation in the temperature, pressure condition, that is means clearly reflected in the particular Raman spectra. So that is how the various geological processes and surface for the various signature can be captured.
Thank you, Dr. Mamta Chauhan, for answering the questions and for your informative talk. Now we will continue. We are going for the break, and we will continue the session at 2:30.
Thank you.
Good afternoon to all of you. Now, welcome to the second session of this workshop on Raman spectroscopy and its application for Earth observation. Now, in this talk, I am going to deliver lecture on applications of Raman spectroscopy in Earth observations and remote sensing. So basically, in this talk, we will explore the versatile applications of Raman spectroscopy in various Earth observation and remote sensing domains. If you will see the use of remote sensing in Earth observation, so several remote sensing techniques have been used for the Earth observation, like optical multispectral remote sensing, then thermal remote sensing, and microwave remote sensing. So several applications have been developed and the potential have been shown. Now the Raman spectroscopy, though the technique is very, very old, but its utilization in Earth observation to differentiate the different bio and geophysical parameters, to retrieve the bio and geophysical parameters. So this application is new. So the main challenge in Raman spectroscopy in remote sensing which people are facing, that challenge is the Raman signal that is very, very weak in comparison to the other spectroscopy techniques. So that this has been not widely used in remote sensing, but like several studies have been carried out for the Earth observation, and the instruments have been carried out remotely to the different places, and there also the data sets were acquired. So in this presentation we are going to explore and to see the potential of the Raman spectroscopy, particularly in the Earth observation, particularly for the glacier and ice, and for the soil application, for the vegetation. So we will try to explore the application in the different techniques. So as we are already knowing about the Raman spectroscopy, because first two lectures were basically focused on the fundamentals and the techniques of the Raman spectroscopy. So as we know that Raman spectroscopy is a powerful analytical technique based on the inelastic scattering of light by molecules, and the scattered light or signal reveals unique vibrational fingerprints of molecules, enabling their identification and quantification. So Raman spectroscopy makes it unique based on its vibrational fingerprint, because based on that it will be possible to differentiate the two molecules based on their vibrational spectra. Now, when we are talking about the advantages of Raman spectroscopy in earth science applications, so first advantage is this is non-destructive. So since this is non-destructive, so it can analyze samples without altering their chemical composition or physical properties. And here, as we have already talked, like the different type of remote sensing like optical multispectral and other techniques like microwave and thermal remote sensing that have been widely used for the Earth observation in different thematic applications. And those techniques are also non-destructive, because those techniques are also not going to alter or change the chemical composition or the physical properties of the objects. Only the thing is the signal strength, because here if you will see the Raman signals, that will be very, very weak in the Raman spectroscopy. So do the Raman spectroscopy from a large distance, from a long distance is challenge, because signal strength will be very, very less. And this instrument can be easily used for the in situ analysis. So it can be used to directly analyze samples in their natural environments. eliminating the need for sample preparation. And when we are talking about the versatility of the Raman spectroscopy, so it can be used to study a wide range of materials, including minerals, organic compounds, and atmospheric gases. So there are several applications of Raman spectroscopy. So I have listed few of them. One is the mineralogical mapping based on the different signal based on the vibrational spectra. One will be able to differentiate the different minerals present in a small sample. And it could also be used for detection of organic and the biogenic materials. And it has been widely used for monitoring atmospheric composition also. Raman spectroscopy has been used for hydrological and the water quality monitoring. And this has also been used for the glaciological applications as well as to find out the ice composition. And Raman spectroscopy has been used to find out the disease in the agricultural crops, and as well as it has also been used to find out the soil compositions. And in the last lecture, you have seen that it has been used for the planetary studies also. Now in this presentation, we are going to see about the strength of Raman spectroscopy in glacier and the ice studies. Raman spectroscopy is a powerful technique used to study the properties of materials, particularly the molecular composition and structure of ice and glaciers. By analyzing the scattering of light, this method provides insights into the chemical and physical process occurring within these frozen environments. Now, the advantages of Raman spectroscopy in ice and glacier analysis has been listed here. So, as we are knowing that this is non-destructive technique, so this is not going to alter or damage the sample. And this could be used for the in situ analysis mainly, that will be helping in the to analyze the ice and glacier samples in their natural environment. And Raman spectroscopy can detect even trace amount of molecules, providing detailed information about ice compositions. Now, when we are talking about the molecular fingerprinting of the ice samples, so here we will see the Raman spectra of ice show distinct peaks corresponding to the vibrations of water molecules, indicating the presence of ice. And it can also be used to find out the impurities like dissolved gases, minerals, and organic compounds, providing insights into the composition of ice. And Raman spectroscopy can also used in differentiating between the isotopes of water molecules, allowing for the study of the past climatic conditions. This is Raman spectra for the hydrogen bonds in the ice IH. IH is basically representing the hexagonal ice crystals, that is the natural form of the frozen water. So here in this study, it has been found that like when there is a relation between the change in temperature and the normalized and the Raman shift. So if you will see, when there is decrease in temperature, when the temperature is decreased from 253 degree to 83 degree, so clearly there is change in the Raman shift, Raman peak. So Raman spectra of ice IH, that IH we have already talked, that is the hexagonal ice with the different temperatures, and it has been recorded in the different vibrational mode. Like V1 here is representing, if you will see the V1 is basically representing the H vibrational mode, and simply V is representing the OH antisymmetric stretching vibrational mode. V negative is representing the overtone of bending mode, and V plus is the OH symmetric stretching vibrational mode. Now, if you will see that there is a shift in spectra, Raman spectra of, if you will see, H2O ice have the strongest band in the region of 3150 centimeter inverse. So here we are going to mainly in this paper mainly the 3150 has been used because this is the strongest band region for the H2O ice crystal. And so that this Raman spectra has been the most suitable technique for studying hydrogen bond dynamics of the ice. If you will see in the different vibrational modes, like A is representing the vibrational mode V, that is the OH antisymmetric stretching, and the second graph is representing V1, that is the bending mode, and the third is representing the V plus, that is the OH symmetric stretching vibrational mode. So in all, what we are going to see that as the temperature decreases from 255 to 80 degree, so there is a change in the Raman shift. So and that change is near to linear. So in this study, it has been found that when there will be change in the temperature, so there will be a change in the Raman spectra. So that change has been studied and that has been used to analyze the hydrogen bond network in the ice IH, and this study I have cited here. So mainly I took it from this study from the paper Raman spectra study hydrogen bonds network in ice IH with cooling. Now another study in which a remote Raman spectroscopy was performed from the different distances. So in this research article that was written by the Rule F et al., the article is analysis of the Arctic ices by remote Raman spectroscopy. So in this article, like from 40 meter, 50 meter, 80 meter, 120 meter, from different distances, the Raman spectra of a glacier of an iceberg was collected. So like here in this image, if you will see the second image, if you will see, so this is Raman spectra which is collected at 50 meter distance, and the Raman spectrum of ice is well known and consists basically on the three internal vibration of the water molecule, V1, V3 and V2, and V3 is representing here OH stretching mode and HOH bending is V2 mode, and there are a few external modes also. So if you will see the Raman spectra, so intensity normalized spectra, if you will see, so this peak we are getting from the ice core. So this Raman spectra is generated, and it has been found that the OH band profile changes indicating structural changes in the ice. These changes affect mainly the relative intensity for the band components observed at 3036, 3366 and 3443 centimeter inverse respectively. Spectral changes observed from target to target can be related with modifications on ice IH structure introduced by the ice formation process and or temperature and the pressure effects. The Raman spectroscopy has also been used in the in monitoring the ice melts and the composition changes. So Raman spectroscopy can monitor the melting process of ice, and it can provide the data on melting rates and changes in the ice structure. It could also be used in finding out the compositional shifts. Raman spectroscopy can detect the changes in the concentration of impurities as ice melts, offering insight into the fate of these substances. Raman spectroscopy can contribute to understanding the dynamic process of glaciers such as flow, deformation and fracture. Now Raman spectroscopy has also been used in investigating impurities and particulates in ice. And Raman spectra can identify the and quantify the impurities in ice, and it can reveal the deposition of the atmospheric pollutants and the dust particles also. And the analysis of impurities in the ice cores provides the insights into past climate conditions and atmospheric compositions. And it can also provide the distribution of impurities that can affect the stability and melting rates of the glacier. So this can help in understanding the overall health of the glacier. Now, this study was carried out by Rene and Russell. And this was carried as a NASA project. So the title of the study was Remote Sensing of Dissolved Oxygen and Nitrogen in Water Using Raman Spectroscopy. So this investigation was conducted to quantify the concentration of dissolved molecular oxygen and nitrogen in water by means of the Raman spectroscopy. Now, the dissolved oxygen and nitrogen both were successfully identified and detected in this study. And in this study, they have proposed remote Raman sensing for oxygen and nitrogen in the coastal water flight experiment. So in this study here you can see that nitrogen filter and oxygen filter, these filters were proposed to be used, and basically 532 nanometer laser was proposed to be used to detect these dissolved oxygen and nitrogen, and with the help of this technique, one will be able to find out the dissolved oxygen and nitrogen in the water from a long distance also. Here the proposed aircraft altitude was kept approximately 150 meter from the sea surface. Raman spectroscopy has also been used for the monitoring and mapping the soil constituents. So clay minerals exhibit unique Raman spectra, providing insights into their mineralogical composition and the structural characteristics. So based on the difference in the Raman spectra, one will be able to differentiate the clay minerals. And Raman spectroscopy also allows for the analysis of the functional groups in the soil organic matter, providing information on its composition and the decomposition stages. And the metal oxide in soil contribute to the Raman spectra, revealing the information about their chemical composition, oxidation state, and the mineral form. Now, these are the different application of Raman spectroscopy in soil analysis: mineral identification and quantification, organic matter characterization, metal oxide analysis, soil structure and texture, pollutant detection, and soil health assessment. So with the help of the Raman spectroscopy, by getting the different Raman peaks that will be contributed due to the presence of different minerals, one will be able to differentiate the presence of different minerals in the soil, as well as by seeing the unique Raman spectra of the organic material, one will be able to characterize the organic material from the soil also. And one will be able to find out the information about the soil structure and the texture, because several studies have been carried out on this also. And if there are the pollutants present in the soil, that could also be measured and detected. Now the overall detection of the these things that will help in the soil health assessment. Now this is a study on the classification of the soil sample based on Raman spectroscopy and the X-ray fluorescence spectrometry combined with chemometric methods and the variable selection. So in this machine learning approaches have been combined with the Raman spectra to differentiate the different soil types. So here 5 soil types were taken and their Raman spectra were generated. So as mentioned in this paper by Luna et al. So from the raw Raman spectra, it was very difficult to differentiate these soils. So they implemented the machine learning based approaches. So this approach which the Luna et al. Developed, they developed by combining Raman spectra with support vector machine SVM method and the genetic algorithm that is represented here by GA for the variable selection. And at the time of validation, they were found that the misclassification error was 0%. So a very highly accurate result they obtained from the use of machine learning technique with the in Raman spectra for the classification of different kind of soils. So this study demonstrated the potential and use of the machine learning tool and the Raman spectra for analyzing and for the detection of different kind of soils. And the accuracy was 100% as according to the literature, because the misclassification accuracy was 0%. In the last lecture also you have learned about the use of the Raman spectroscopy and mineralogical analysis. So Raman spectroscopy can identify the different minerals based on their unique vibrational spectra, because different minerals, they will have their unique vibrational spectra. Based on that, one will be able to match the obtained spectra with the library, so that the one will be able to clearly identify the mineral. And it can also differentiate between the different crystallographic phases of the same mineral. So this will also help in analyzing the phases of the minerals. And it can be used to determine the composition and distribution of minerals in rocks and soil. So it will be used in the geochemical studies also. Now I am going to show you here the use of again machine learning tool in the Raman spectra for the mineral classification under low signal dusty marsh condition. So the study was carried out by Berlanga et al. So in this study, they had used the several techniques to identify to identify the different minerals. So this study examines the Raman spectra of the common rock forming minerals, including silicate, carbonate, and sulfate types under low signal to noise ratio and conditions similar to those on Mars. So the several spectra were taken. Approximately 5 lakh spectra were used to train the model, and finally when different machine learning approaches were used, so in the different mineral classes from 0 to 50% of dust covered granite and the gabbro. So it here you can see that K means clustering, that is for the 0% dust cover of granite. This is showing the 13.92%. Random forest is showing 45.82. Linear SVC is showing the 54.65. Logistic regression is 63.90. Multiple linear is showing the 89%, and highest accuracy is achieved through the convolutional neural network CNN. The approximately similar kind of results were obtained for the case of the granite with 50% dust coverage. So here CNN again performed gave the best result with 81.18%, and the second best was MLP, multiple linear based regression provided second best result, and random forest only provided 39.34. Similarly, when you will see for the gabbro with 0% dust coverage, so again here also 99.40% accuracy was achieved with the help of the CNN, and MLP provided 87.35% accuracy, and with 50% dust coverage of Gabbro, again CNN provided 80.39%. So here in this study, they concluded that minerals could be classified with the help of the CNN very accurately in comparison to the other modeling approaches, other machine learning approaches. Now, this is the Raman map of garnet crystal. So, in this map here, you can see that this includes the quartz and calcite in the core. So, basically here you are going to see the one zoomed portion has been shown in the image B. So, this image has been generated based on the Raman spectroscopy. So, now based on the different peaks of the Raman spectra, these minerals were identified, and they had one image has been generated that is based on the classification. So in the image, if you will see, the green color is basically representing the quartz, because for a quartz we are going to see one special peak near to approximately 490. Okay, so the green one is representing quartz, and garnet is represented in the red color, because again we are getting the Raman shift peak in these locations. And if you will see the calcite and the aragonite, so maximum peak we are observing near to 1090 or 1080, 1090. But again, when you will see that for in both the cases, calcite and the aragonite, it will become difficult to differentiate. So, but some other small peaks were also observed. So, based on these two peaks, these were differentiated. So, if you will see the aragonite, so this is represented here, shown here in the yellow color, and the calcite is shown in the blue color. So, here you can see that entire map of the garnet crystal has been generated here, and in which quartz, garnet, calcite and aragonite has been clearly identified in the crystal. Now, Raman spectroscopy has been used for the organic compounds, particularly for the plant biology, for the biogeochemistry and for the environmental monitoring. It has been used to find out the plant health and to monitor the plant growth and to find out the composition of the plant. Now, in this study, portable Raman leaf clip sensor for the rapid detection of the plant stress. This study was carried out by the Gupta et al., and this study was published in the scientific reports. And in this study here, you can see that several leaves were taken for the 5 different vegetation, and their images are also shown here. And here you can see that their spectra was generated. So, based on the Raman spectrum of the carotenoid chemical standard, 520, 1150 and 104 centimeter inverse peaks were identified in all tested carotenoids. So, here the similar kind of peaks were identified for all the for the different type of species. And the observed Raman peak at 1520 is due to the CC stretching, that is the vibration B1. 1150 centimeter inverse peak is again CC stretching vibration V2, and the weak peak at 1004 centimeter inverse is due to CCS3 stretching. And this has furthermore the measured Raman spectrum of the potassium nitrate and the ammonium nitrate showed a peak at 1046 centimeter inverse, indicating that this Raman shift is indeed the nitrate peak. Now, this Raman spectra was collected for 2 different tree leaves of the different species. And when the Raman spectra were generated, particularly this Raman spectra were generated in the laboratory of Raman laboratory of the UPES. So here we can see that blue line is representing the sample of leaf 1, and the red line is representing the sample of the leaf 2. So based on the Raman spectra, one will be able to find out the difference in the two species of the vegetation, because here we can see that there are 3 different peaks were observed here. The one peak at 1008 centimeter inverse, another peak as 1156 centimeter inverse, and the third peak at the 1520 centimeter inverse. Now if you will see that the difference in peak, so leaf 1 is showing the higher intensity in comparison to the leaf 2. So when we try to analyze based on the literature, so we had put the analysis of the leaf 1 and leaf 2 here. The spectrum of leaf 1 displays the distinct peaks around 1008 centimeter inverse, 1156 and 5020 centimeter inverse. The peak at 1008 centimeter inverse correspond to the CC stretching, vibration in the cellulose and the lignin, which are key components in the plant cell walls. The peak at 1156 centimeter inverse is associated with the CH bending vibrations often linked to aromatic compounds. The peak at 1520 centimeter inverse correspond to the D band associated with the disordered carbon structure or the aromatic ring breathing vibrations. Because these observations we made based on the available literatures. Now when we talked about the leaf 2, so the spectrum for leaf 2 shows the peaks at the similar wave number but with varying intensity and the shapes. So the 1008 centimeter inverse peak is prominent but may differ slightly in the intensity compared to leaf 1. The peak at 1156 centimeter inverse is also present and shifted to some degree, indicating difference in the molecular composition of the leaf. The peak at the 1520 centimeter inverse is more distinct, possibly due to the variations in the lignin or the polyphenolic content between the two leaves. There were some more analysis on this, but these were the major analysis which we done with the help of the two spectra of the vegetation leaves. Raman spectroscopy has also been used in the atmospheric study. It can measure the concentration of the gases, including greenhouse gases like carbon dioxide and methane. It has also been used for the aerosol analysis. It can analyze the composition and the size distribution of the aerosol, which play a role in the climate change. And it can study the properties of the clouds, including their composition, temperature and size. Raman spectroscopy has also been used in the aquatic and the marine environments. It can detect and quantify pollutants such as the heavy metals and the pesticides. It can analyze the composition and distribution of the phytoplankton, which are the primary producer in the aquatic ecosystems. It can study the role of organic compounds in the marine geochemical cycle, such as the carbon cycling. Now, these are the advantages of the Raman remote sensing. This is non-invasive. So remote analysis without disturbing samples could be done. The high specificity differentiates closely related molecular species and enhances data from the other spectroscopic methods. In some studies, it has also been, I read some literature based on the hyperspectral Raman remote sensing, and that was beneficial in identifying the closely related minerals for which sometimes it becomes difficult to identify based on the spectroscopy. So hyperspectral Raman spectroscopy has been used to resolve the problem which the people are facing with the normal spectroscopy. Now the challenges are also there with the in Raman spectroscopy, because weak Raman signals often require enhancement techniques. So there is requirement of the enhancement techniques, because when we are working with the restricted environment, so we can get the perfect results. But when we will have to work in open environment, so enhancement techniques are required to get the clear Raman spectra of the object. Environmental factors will highly influence the spectroscopy technique. So again, if one wants to do the Raman remote sensing, or one wants to work with the remote sensing Raman sensor based remote sensing, then at that time it will be required to enhance the signal, because environmental factors, they are going to influence and they are going to disturb or contribute as a noise in the signal. And the real-time large-scale remote sensing needs the advanced instruments, because definitely when we will have the art of the state sensor in Raman spectroscopy, then only we can plan to put in the or use the remote Raman spectra as a remote sensing technique. Now we are going to conclude the lecture and the future prospects. So Raman spectroscopy has emerged as a powerful tool for Earth observation, and we have seen the few examples of the Raman remote sensing, in which the spectra were collected from the 40 meter, 50 meter and 100 meter distances, offering numerous advantages for addressing environmental challenges. With continuous technological advancements, Raman spectroscopy holds immense potential for the future applications, including real-time monitoring, precision agriculture, and planetary explorations. Now, thank you for attending this lecture. Now, I would invite a few questions from the audience side. And we can combine the questions in both the classes. Dr. Som Kumar Sharma sir. So he is a prestigious and very famous scientist in Raman spectroscopy using Raman lidar, particularly for the atmospheric science perspective. So I request Dr. Som Kumar Sharma sir to deliver his talk.
Very much, Dr. Sasikumar ji. It is truly a pleasure and privilege for me to be present here in this DLP conference room, which is decimating so much knowledge to millions of young, desired, or you can say thirsty people of knowledge in India. And at the outset, I would like to thank Professor R.P. Singh ji, Director IIRS, who was instrumental to bring me here in offline mode. Thank you to Group Director Sefali Madam and Course Coordinator Sasi Kumar ji, who has made all the things you can say possible for me to be here and to present whatever little I could do and doing in the field of Raman lidar for the investigation of Earth atmosphere. So with this preamble and thanks for nice introduction, I will move ahead, and the topic, as you know, that it is very much overlap with your today's workshop schedule, that is Raman spectroscopy. So the two things, if you see here, they are in the blue: Raman spectroscopy and how it is useful in the atmospheric science. And of course, there should be couplers, and these couplers are like Raman lidar. Okay, so this specifies that what I am going to present. But before I go to the topic, I belong to a very historical and very prestigious, renowned national and international institute, that is Physical Research Laboratory. Many of you may be knowing this was the first institute in India which was established by a great visionary Dr. Vikram Sarabhai, and from there all the things for the space science started in 1947. And after that, the DOS, ISRO, everything is started from PRL. And now you know that we have so many activities, so many institutes in India under umbrella of DOS and ISRO. So this is a map of India, and in map of India, on the western part of India, there is a Gujarat and Rajasthan, and in that there is a two centers, or you can say main campus of PRL is a PRL main campus. This is little, you can say, about our institute where we are working. And then another one is a Thaltej campus. It's near to PRL, where we develop our payload for Aditya L1, Chandrayaan, Mangalyaan, and all these things, along with the SAC, of course, with the ISRO. Everything, whatever I am going to talk, it is under umbrella of DOS, Department of Space, and various ISRO center. I want to say in the beginning itself, because everything is a collaborative mode. And then in neighboring state, there is a Rajasthan. The two beautiful campuses we have in two beautiful and you can say tourist place cities of Rajasthan. One is Udaipur, that is we have the Udaipur Solar Observatory in the middle of the biggest lake in Udaipur, Fateh Sagar Lake, that is for studying the sun. And another one is on the highest peak of Aravalli range of mountain, Guru Shikhar, that is in Mount Abu or near to Mount Abu. There we have our astronomical observatory, as well as we have there our atmospheric science observatory, where we established India's first lidar way back in 1996. So this is like about PRL, 4 campuses, and PRL investigates all the you can say academic activities and work starting from deep of the ocean to the deep of the universe. So you can visit our PRL's website www.prl.res.in for various activities and opportunities for young people for doing PhD, PDF, project, and MTech, etc. Big is beautiful. So this I am taking close to the your Mount Abu, the Guru Shikhar. This what you'll see. This is basically our astronomical observatory. This was the biggest in IR range, 1.2 meter. And behind this you see we are piggyback, that is our atmospheric science observatory for doing all the optical passive and active remote sensing, including our LiDAR. But this place demography has changed now. Now we have set up another observatory, which is a 2.5 meter telescope, and that is now again the Asia's like that second biggest. Okay, so then you said demography has changed like that. Very recent picture, we went for IC meeting there. So our colleagues are there from PRL, Professor Subhavati, Professor Nandita, and that you see that now we have the series of telescope, and the total there are 6 telescopes from here to here. So this is managed by ISRO for satellite tracking, and then we have our different type, different sizes of the telescope, and this is the second biggest in the Asia. And I will give you the very close view. You can see this is the place. So this was an old observatory, 1.2 meter, and this is the big 2 meter observatory. And by using these observatories, the India has become like they joined the club of discovery of the exoplanets. So that PRL, or you can say the under umbrella of DOS and ISRO, the PRL has discovered at least 3 new exoplanets by using these facilities and by making the in-house instruments, spectrograph, etc. So this is, and then again the taking you into the lake. So this is a beautiful island in between the lake, and there we have, and this again is a biggest in the Asia. It is a MUST, multi-application solar telescope, that is for investigating the sun. Okay, so this is a for study of the solar thing. And now I am jumping to our field. So as I told that Raman spectroscopy or Raman lidar or Raman technique or Raman effect will be used. How can be used for atmospheric investigation? So for that, first thing comes atmosphere. What is atmosphere? This slide is very close to my heart. Here the full atmosphere is embedded. Okay, along with you can say our gadgets. Gadgets means where we do not live, but our essential gadgets are living. So this is the lowest part is there where we live in the planetary boundary layer in the troposphere. But if you go above that, there is a stratosphere, mesosphere and thermosphere. You see that each and every part of the atmosphere is directly or indirectly related to us, and we cannot live without this, because we cannot imagine life without satellites nowadays. It is essential part of our you can say day-to-day activities. And this red line shows the temperature structure of the earth atmosphere. In troposphere it decreases, in the stratosphere it is increases, and in mesosphere again it is decreases, and thermosphere again it is increases. I will not go in the detail because this will deviate from the topic, but this is atmospheric structure, and on the basis of this the atmosphere has been named as a troposphere, stratosphere, mesosphere, thermosphere and exosphere. And in layman's language, suppose someone want to know that it is difficult to remember tropo, strato, meso, so we have classified the lower atmosphere is up to 10 kilometer or so, where you can say lower, truly the lowest part. And then if you go up, then it is a middle atmosphere, that is from 10 to about 90 kilometer or so, and then truly it is upper atmosphere. But if you see this part of the atmosphere, lower, middle and upper, they are not living independently, just like our body part. Left hand does not live independently, it is always connected with the right hand, and same with the eyes and all part of the bodies. So similarly in the atmosphere also, the lower atmosphere talks with middle atmosphere talks with upper atmosphere, and other way around. So they all are coupled. That's what there is an intersection. These are drawn scientifically, so they are interacting, and this interact stronger. That's what more overlap. This is stronger, little less, because their densities are less. So lower atmosphere talks with middle. So there is a lower to upper coupling and upper to lower coupling. So this is a very brief introduction about the atmosphere. And basically with the Raman lidar, we mostly able to probe the lower atmosphere and a part of the middle atmosphere using the Raman technique. And of course, with the lidar, lidar means different type of lidar, like rail lidar, we probe the atmosphere up to 90 kilometer, means full lower and middle atmosphere. Okay, so that is about that. Now you know about the atmosphere, but for probing the atmosphere, tools and techniques, and the center where we are sitting, it is IIRS, Indian Institute of Remote Sensing. So if I do not talk about the remote sensing, what is the remote sensing in layman's language, then I will be, I think, fall short in my topic. So remote sensing is a very simple thing, sensing remotely. I will say sensing remotely. You do not go there, you send some part of the signal, and that brings back natural information. Please remember, proper remote sensing, natural information. Information should not be modulated or altered. It should come in as natural form as possible. And the remote sensing is of two types, passive remote sensing and active remote sensing. In the passive remote sensing, it's like you do not send any signal, just sit quietly and collect naturally occurring signal. And the best example is astronomy. In astronomy, we do not transmit any signal. We are just collecting the signal which is coming from star, galaxies, nebulas, and so on and so forth. And we are coming to know all the properties, information, composition, temperature, shape, size, distance by just collecting the light. That is a passive remote sensing. The best example, there are so many examples of the passive remote sensing, and I can give the simple example by seeing each other is also a passive remote sensing. Okay, and then active remote sensing, where I belong to and I love it, radar and lidar. Active remote sensing means when you transmit some signal and due to that transmitted signal the information comes back, and the information brings back lot of information. And if you go in the optical domain, if any light passes through the medium or any part of the atmosphere, then absorption, attenuation, scattering, reflection and transmission, these are the optical processes which are taking place, and all of them we are exploiting for our atmospheric investigation. And the best example of the active remote sensing are the two, radar and lidar. Radar is a radio detection and ranging. These are 5 magic letters: RADAR. RA for radio, D for detection, A for and R for ranging. But radio wave has their own limitations because you cannot go beyond the certain wavelength. So you want to probe the molecular size or atomic size, then you cannot probe with the radio beams. You need to go to the similar probe, and then similar probe is a light, because light has a very small wavelength, and these wavelength probes very precisely any part of the atom and atmosphere, you can say. So if you replace RA by LI, then it becomes lidar, light detection and ranging. It's not very far from you. So how to explore the lower and middle atmosphere? You can fly the balloon in situ. There are several limitations, I will not talk. You can fire the rocket for lower and middle and upper atmosphere. There are again limitations. Then you can use the radars, and then of course the ground based lidars. Limitations but so many advantages, and nothing completes unless we go to on the satellite platform. So whatever activities are being done, as Professor R.P. Singh ji in beginning he told like that, there will be definitely sooner or later we have to be, our ISRO has to bring the mission for space based lidars, and in that Raman lidar of course could become a part in the future. So everything completes when we go to satellite platform, because satellite probes the global things and gives the global picture. And this is a word of beautiful word of lidar. As colorful slide I have made, and it's more colorful, or it is more colorful means it gives so many facets of the atmosphere. So lidar is a light detection and ranging. And then there are few things I wrote. So earlier I was saying what you can study by lidar, but now my perception has changed after working more than 20 years in this field. What you cannot study by lidar, there is nothing which we cannot study by using the lidar. Everything you can in the atmosphere you can study by lidar, by proper selection of the laser beam and instrumentation and shape and size and everything. The PRL was a lead institute, and as I told, everywhere it has taken lead, like starting the space science programs in India by Sarabhai. So we were the first in India to establish the middle atmospheric lidar, and that lidar, if you can see here at Mount Abu, it was established in 1996. And since then it is operational. So we have longest series of data in India, and later one second one was developed established with the Japanese collaboration in NARL, National Atmospheric Research Laboratory, which is again a DOS institute near Tirupati. That was in 1998, and we are strongly collaborating. So here you can see there are 2 telescopes. This is for upper atmosphere, means this is up to 90 kilometer, and this is below 20 kilometer. And this our lidar is RMR. It is Rayleigh, Me and Raman lidar. So we operate it in all 3 modes. You can see I am standing here. I was very young that time, about 20 years back, and we have taken almost thousands nights of observation over Mount Abu. Then when I used to be in Mount Abu, then cloud used to be basically, you can say, our enemies. We wanted to probe the 20 to 90 kilometer middle atmosphere, and whenever clouds were coming, we were sitting idle because we were not having any signal, because we cannot pump the laser. Laser will not go above 20 kilometer if there are clouds. So then I made the plan after completing my PhD, and also why I should not study the clouds itself. If there is a lidar available, then we customized the lidar, and we started the working on the new project in last 1 decade or so. That is a ceilometer lidar, which is a low power for studying of the cloud and boundary layer. But we did not stop there. As you know that always scientists are thinking like that, something new and something more need to be done. Then that about 7 years back we have customized and procured one Raman lidar, and that is India's first multi-channel Raman lidar, and when we procured it was 7th in the world. That is a 7 wavelengths simultaneous. That is the beauty. I will tell in the detail, and that is a housed in PRL Ahmedabad. That is the Pota cabin type of laboratory for studying the various thing into the atmosphere by using the multi-channel dual polarization Raman lidar. It is multi-channel dual polarization Raman lidar. It is there. I'll just take this one pointer. Yeah, laser point. Okay. So that is a well, and then again this is our lidar lab. These are the smaller telescope, big telescope. These are all the things we study, and this is a closer view of our Mount Abu laboratory. And then the lidar, basically what is relay lidar or Raman lidar or any type of lidar, they work in the similar fashion. We have laser, we are pumping, and with the telescope we are receiving, and then lot of electronics does the so this is a simple structure of the transmitter, receiver, and then receiving. And then for taking the vertical information, that is very simple principle is being used, which we study in very early classes. Distance is equal to velocity into time. So here it is time of flight is equal to range, altitude r, so c into delta t by 2. So like radar, lidar is also only measuring the time difference between the transmitted pulse and received pulse, which is backscattered from different species, whether it is Rayleigh scattered, Raman scattered, or me scattered, whatever it is, but the principle is same. And the life is not so simple as shown here. When you go in the actual one, there is a lot of noise and all these things are there. So these has to be removed, the singular has to be clear, and then we can do the targeting that has been shown. Of course, there is an interference by aerosols and cloud. Then we take care when we try to study about 20 kilometer and so. Now I am coming to the topic. As Professor R.P. Singh ji has told in the beginning, basically the scattering is a major category of the scattering is two types. One is elastic and another is inelastic scattering. So he has nicely explained that, and I should be thankful whatever I am going to talk, Professor Thakur and Ranjit Singh ji and Shashi Kumar ji all has gave you the basic, you can say all the ingredient what you want to know about the Raman spectroscopy. So my foundation has been made by them. That's what I can go a little faster, because these are the things you have already been told my previous speaker. I am thankful to them. So elastic scattering is that you can see the elastic scattering like absorption, fluorescence, all this, where there is basically wavelength do not change after the scattering. That is elastic scattering. And as Thakur Sahab has nicely explained, that like that there is no polarization happens, and like that whatever wavelength you send and at same wavelength you receive the signal. That is basically elastic scattering. But when there is inelastic scattering, then what happened? The shape of the due to the electrical nature of the light, because light has electric field and magnetic field, it interact with the electric and magnetic or electrical vector of the molecule, and that it basically what happens, it got elongated one side, then charge separation takes place, and due to that there is a very small scattering takes place, and that is the Raman scattering. And this is basically depend upon the material. Please remember, that is dependent on material, and that's what the Raman spectroscopy is very useful. So you see this is elastic scattering, and here you see elastic and inelastic both has been shown. So this is the Rayleigh scattering, that if you see spectroscopically the excitation takes place, go to this virtual level, and from same level there is a emission. So that is Rayleigh one. But here if you see very simplistically I have made it like that, if the signal goes to a virtual level and it comes back, but it is not coming to the ground level, it comes to the fine structure, you can say super fine structures here. So then there is a basically this is a Raman line, and the Raman line is not like that it can stop. It depend upon the molecular structure or atomic structure of the molecule or either material. So it can, if it is this also is Raman scattering, if it stops in this level then also it is Raman scattering. And of course absorption and fluorescence is shown here. That is not today's topic, I will not discuss, but focus here is like that. That's what the Raman scattered wavelength is unique to the molecule. I will come to that. I will explain these things more. And if you see that how the temperature wise these things are changing, these are shown here, and this is basically, so I am sorry for poor reproduction, this is a Rayleigh signal, okay, Rayleigh or me signal. So I'll explain these things in little more detail, but as I am a LIDAR man, so the LIDAR, basically I'll not go in all the mathematics, but the LIDAR works on the principle like that, mathematical LIDAR equation. And LIDAR equation is nothing, whatever power you have pumped and how much power you have received. And when you are receiving, then it is received photons. Okay, and these are basically this is a transmitted photon. Okay, this is related to laser power, but then these so many things, and this is basically receiving probability, as I was just talking to the RP sir. So this basically this is power and this is aperture. So the power aperture product is only in our hand if you want to maximize this one. For maximizing the received photon or received power, the power and aperture we can play, and both are tricky to play in the either it is in radar or in the LIDAR, and these other things are not in our hand. So these all are related to the atmosphere, the number density, and there is scattering cross section, noise, and so many things, and LIDAR efficiency. These are not in much in our hand. So this is a very simplistic view of the LIDAR equation, how it relates to the atmosphere with the system. Now I am coming like that, why the Raman spectroscopy, Raman LIDAR, or you can say Raman things are little difficult to use very effectively, or you can say very widespread use, like because the Raman scattering cross section is a very small. If you see here, just all scattering cross sections are written. You see me scattering, which is taking from aerosols, or you can say in layman's language dust particles. So the scattering cross section is a 10 to power minus 8 to 10 to power minus 10 centimeter square per steradian. And the 2 photon process, I'll not go in that in. This is mechanism, of course, physics. And then atomic absorption resonance is 10 to power minus 13. Then molecular absorption 10 to power minus 19. Then fluorescence, which takes place from molecular liquid solid 10 to power minus 19. Absorption and fluorescence almost scattering cross section, back scatter cross section almost same. Rayleigh scattering, which we are using for the deriving the atmospheric temperature up to 90 km using the LIDAR, that is of the order of 10 to power minus 27. But if you come to the Raman scattering, it is 10 to power minus 30 to minus 32. The range is that, because here it is normally is not fixed, 10 to power minus 32 must depend upon the molecule, and that basically Raman scattering, it is a wavelength dependent, please remember. And this is, as Thakur Sahab has very nicely explained, it is a 2 photon process, and it is inelastic scattering, where the wavelength changes after the scattering. That is a beautiful things, and you already he explained, so I will not repeat it. What is the two photon process? He nicely explained it like that. So that is basically the Raman scattering cross section. Then this slide again I love a lot. Here all the 3 component, as I told that societal perspective is very important. So the first column what you see, this is basically physics, okay, science part. This one is a technical part, means engineering section, and this what we give to the society by using the suite of LIDAR. So elastic scattering is a physics thing which is taking place from aerosols and clouds, as well also from molecular these things. I will come to that. And that the instrument we use is LIDAR, and we give aerosol, cloud, geometry, thickness, and so many things. Absorption by atom and molecule is a physics related, and that is dial, differential absorption LIDAR. DI for differential, A for absorption, L for LIDAR, for study of the gaseous pollutants and ozone concentration in the stratosphere. Then inelastic scattering comes, and that is basically Raman LIDAR. It's today's topic. So it gives the water vapor, ozone, aerosol, cloud, optical density, and temperature in the lower atmosphere. That is the key. Basically, it is very difficult to derive the vertical profile of temperature in the lower atmosphere continuously. Okay, that you can do by using Raman LIDAR. Then elastic scattering by air molecules is a Rayleigh LIDAR. Is you can calculate the stratospheric, mesospheric density and temperature. And then of course there are so many things, and recently the Doppler shift is being used for wind LIDAR, and so many things. I will not go in the detail because there are so many other things. Again, if you see that basically spectroscopy wise, like that, Rayleigh scattering, Raman scattering, and resonance scattering. The processes involved in the interaction of incident optical radiation and molecules, you see that when how the infrared radiations are absorbed, then this is Rayleigh scattering. Here you see that strokes and anti-strokes, like that the Raman scattering, and then resonance. So this one is for resonance, please, like that. But you see this here, that is Raman scattering, I'll not go in much detail because this has been already talked by the our earlier speakers. But these are basically Rayleigh, Raman and resonance scattering. If you see spectroscopy, they look like that. So Raman scattering you can see here. This like Stokes line and anti-Stokes line are being, you can say, pumped back and we are receiving it. Now, as I told that it is Raman scattering is basically it is specific to the molecule or material. That's what it has a lot of usefulness. You see here basically I have shown here the three laser wavelength. This is 532, 355 and 266. This is a 532 is a green. This is ultraviolet, near ultraviolet, and this is harder ultraviolet. So 532, 355, 266 and these are derived from Nd:YAG laser where the fundamental is 1064. So from 1064 you can double the frequency, our wavelength becomes half 532, triple it is 355 and 1/4 is 266. So from same laser we are deriving these wavelength. But if you see, if you pump that 532 into the atmosphere, then from oxygen, here you see the oxygen molecule, this oxygen molecule you will get Raman backscatter signal at what wavelength? 580. Same wavelength if you have the receiving channel, as I told, multi-channel, from nitrogen you will get signal at 607 and from water vapor you will get at 660. So you are pumping 532, if you put the 3 PMTs, 580, 607, 660, you can simultaneously you can record the nitrogen oxygen signal, nitrogen signal and water vapor signal. But suppose if you pump if you have laser with 355, then same molecule, that oxygen will give signal at 376, nitrogen will give at 388 and water vapor will give at 407. And that where there is a multi-channel receiving is a very important for simultaneous study. But if you go to 266, then Raman backscatter signal you will get from oxygen at 277, from nitrogen at 284, and so these all are molecule dependent. You can have same wavelength, but you see the multi-molecule you can study, and that's what it is. Raman is a probe. You can probe it wherever you want. You can probe. I can give simple example. Suppose in one class there are 20 students. So Rayleigh scattering me scattering can tell there are 20. Number can tell. Our radar can tell. But if you want to know how many boys and how many girls are there, so Raman technique if you use, it will tell that how many boys are there, how many girls are there by remote sensing. So that is that way I can explain to the layman how the Raman technique is very useful for investigating the atmosphere. As I told, below 20 km is very difficult to derive the temperature profile by using the LiDAR, because LiDAR uses the two assumptions. Rayleigh LiDAR uses the two assumptions. Atmosphere is in hydrostatic equilibrium, number one, and number two, gases in the atmosphere are ideal gases, and that ideal gas condition is fulfilled only by nitrogen and oxygen, natural gases. But the atmosphere below 20 km is contaminated by the clouds and aerosols. So you cannot derive the temperature by using Rayleigh LiDAR below 20 km. So for that we are using the Raman LiDAR. When we pump the signal, then how much signal is coming from nitrogen? We know this is nitrogen density and this is oxygen density. It will not come from aerosol and cloud. So this you see that Rayleigh plus Raman integration if you do, then we can get the signal from 0 to 100 km. So this is the beauty of, so this is basically from Rayleigh, hydrostatic equilibrium and ideal gases. This you do. So the density ratio gives the temperature, and but if you use the Raman LiDAR, so you can get the vibrational rotational Raman line by using the Raman LiDAR. It gives the only nitrogen and oxygen, and that is a representative of neutral density. So you can make the neutral density profile. From neutral density profile you can use these two equations and you can derive. Here pressure is related to density. So from density you derive the pressure, and from pressure you can derive the temperature. So this is a simple equation for complete atmosphere if you know complete neutral density profile. And below 20 km we are using Raman, and above 20 at Mount Abu, above 20 km we are using the Rayleigh. So this is a beautiful technique by due to Raman effect. Then another very important thing like that, which is basically for clouds, the water vapor is the most important component. We cannot live without, you can say, the water, and water can be brought only by the clouds, and so the clouds are formed mainly due to the water vapor if adequate amount of water vapor is present. So and water vapor is highly variable regionally and seasonally. So for that, the Raman lidar we are using at Ahmedabad, that water vapor, how the water vapor is changing from time to time. So there you can see it's a relay signal. This is O2, N2, and all things we are studying together. This is the beauty, the multi-channel. Relay signal we are receiving signal from O2, we are receiving signal from N2, and we are receiving signal from water vapor. And this is only possible due to Raman lidar or due to Raman spectroscopy. And then we are deriving the profiles by comparing that. And this is the closer view. You see that this is basically lidar. This is a relative humidity by the balloon, but balloon can give once in a day or twice in a day. But this balloon, and then you can calculate that how much is a correlation is there, and you can get the water vapor mixing ratio. Then as explained by Professor Eten Thakurji in the morning first talk, that benzene basically that it is a pollutant. If it is in atmosphere, it is a pollutant. So benzene gives very beautiful signal, and that can be studied by Raman. So you can get the different signals. You can say these peaks are there from Raman scatter from benzene. So different wavelength you can get, and you can study wherever there is a benzene contamination. You can investigate by using the Raman lidar. Now I am coming closer to the societal perspective. If you have the pollution plumes, in that pollution plumes, it is very difficult to prove any new pollutant has come or not. Whatever is O2, SO2, H2S, ozone, and so many CO, their pollutants are there. So you can by using the Raman lidar and differential absorption lidar, both you can use, and you can put it like that very strong. And in defense, we are collaborating with the defense sector. When there is a nuclear, this is chemical war type of thing. In chemical war, what gases are using and what gases are coming out, then these Raman lidars are very useful. You can pump the Raman lidar, it will tell what gases they are pumping. So this type of signal you can get, and then you can analyze that. Simple principle is same. Then you can analyze these pollutants are due to using the Raman spectroscopy, which gas is available in the chemical gas attack. Or you can say in the firefighting, whenever there is firefighting, what type of gases are coming. So these gases are representative to which type of material they are using in the guns or in this thing. So this is basically lidar application for pollution monitoring. And then you know that in the atmosphere there are several you can say type of aerosols are there. There is a sea salt aerosol, there is a sulfate aerosol, there is a biogenic aerosol, there are anthropogenically produced aerosols. So in these aerosols also, by using the Raman lidar, by calculating the lidar ratio and depolarization at different wavelength, you can pinpoint it is whether the plume is there, whether it is a Saharan dust, mixed Saharan dust, Canadian biomass burning, African biomass burning, anthropogenic pollution, marine aerosol, and India we are doing in the Western Indian region. That paper is under publication. So this way you can tell that in pollutants also what are the region of what is the local production of pollution and how much is transported from the sea and from other countries. That all the things you can very precisely do by using the Raman spectroscopy or Raman lidar. The same thing you can see, you can pinpoint their concentrations. Dust, smoke, volcanic ash, dust, and then dusty mixture, then ash, biomass burning, then marine, then pollutant, then smoke. So all the things you can quantify, and these are by using the lidar, ratio and different polarization and at different wavelength and using the Raman technique. I am coming to the forestry, as I told that atmospheric science perspective, and the forests are also a very strong component of the. So for this, that is not of course Raman, but Raman can be used in this. Lidar application for forest study, you can canopy study you can do. In that canopy, basically I am working on that. If time permits, then basically soon we will be developing the system. If put the Raman lidar on the small you can say this our drones, and on the drone this is being used for only canopy, how much forest cover is there, what is the height of the forest plants and all this, then what is the different type of vegetation in the plants, because the different type of vegetation will give different type of Raman signal. Okay, and how many leaves are brown or how many are black, how much dust is sitting on that, these all the things you can quantify using the Raman lidar or Raman spectroscopy or Raman technique in the forest also by using the drone, because now the drones are there, and drone you can fly very close, so the distance is very less, then signal will be very strong. so that you can study. And then you can canopy height, ground elevation and all those things as I told na. Here I have just made the green color, taken the green color, but different colors will give different Raman signal. And that Raman signal can be used for different type of vegetation inside the deep forest where you cannot go. It is difficult to go in person or to study in situ. That can be done by beautifully by using the Raman lidar. Even you can count the this idea I took. Even you can count how many leaves are like about to fall and how many with leaf and without leaf. That you can even count with the Raman lidar, because it is very focused and very precise tool is there. So with that you can even in plantation like that you can say how many leaves are about to fall. Then you can do that type of thing. The leaves are going to fall. This type of leaf are mature leaf. These are immature leaf. And that R.P. Singh ji and his group was doing for crop monitoring from satellite in SAC. We know that in the from satellite like that what will the yield and all the things can be. So these what being done from satellite, but nowadays the drone can do, small Raman lidar can be put and you can fly it, and like that color mapping and all this you can do. Then you can do very precise and regional crop mapping, how much crop is going to happen and all these things. This we are planning, but of course it depend upon the how much time I have like that. So I'm coming to my favorite topic, how the clouds we can investigate and new discoveries what we have done from Indian continent for using the Raman lidar. So you know all that cloud is an essential part of hydrological cycle, that we all know. It is direct impact, and if you go to the indirect impact, they basically clouds are modulator of the radiation balance. Some clouds are warming the atmosphere and some clouds are cooling the atmosphere. Cirrus clouds are cooling the atmosphere, and the stratus and cumulus cloud are warming the atmosphere because they are not allowing the long wave radiation to go away. And cirrus cloud is not allowing to come properly the short wave radiation which is coming from the sun. I will not go much detail in that one. This is a closer view of our India's first multi-channel dual polarization portable Raman lidar. You can say this is a lidar in operation. It is housed in this porta cabin. This is a laser beam. Green you can see, but we are pumping the 3. Basically we are pumping 1064, 532 and 355. So 1064 is in IR, you cannot see here, not seen, and 355 is an ultraviolet, you cannot see, but green is 532 visible, it is seen. So all three are pumped collinearly. And then this is a magic, you can say. This the transmitter signal, all three are going, second harmonic, third harmonic and principal, 1064, 532 and 355. All are pumped collinearly, and this is a beam expander. Expand the beam, it is pumped, and then we are receiving. After receiving, the receiver is a magic box where we have channel 1, channel 2 and channel 3. In channel 1, we are receiving like that the 2 wavelength, 3 wavelength, 3 wavelength and then last 1 wavelength. So total 7 wavelength. So 2 elastic, 532 and 355. In the cross polarization, it becomes 4. Then at Raman, 607, 407 for water vapor and 385 for nitrogen. 607 for nitrogen. So all 7 are collected together. That is a beauty. All are coming together, and then we do the analysis. Rest as I explained like that. So this is basically receiving at different wavelengths. So we have basically total 7 wavelengths. 5 are seen here, 2 are not shown because they are cross polarization, the linear and parallel polarization for calculating the color ratio. This is a first picture, paper soon will come, and this is from Raman lidar. At different wavelength you see this is a complete troposphere over Ahmedabad. This is the first in India. You can see that all the things you will see together. That you see this is the growth of the aerosol. This is the local time. You see the growth of aerosol, how aerosols are growing over Ahmedabad during daytime. You can see this one. And then these are like that. These you may feel these are clouds, though these are not clouds. These are basically the aerosol layers which are that drifted away, and there's a wind has taken them like that. So this one is there. And these are the mid-level clouds. You see, these are the mid-level clouds. These are high level cloud, these are cirrus clouds, and part of the cirrus cloud, and this is the downdraft of the cirrus cloud. You may surprise this here there is a noise. You may guess this is a noise, means this is when sun is directly looking towards our telescope. So that time our PMCs are saturated. So this I have not removed deliberately. Why? Because it's showing the system is working very perfectly. So this time SNR is very poor because here signal is very strong. That's what you are not getting. So all the things together, that is a beauty. The multi-channel beauty is like that. Everything is together. Whatever you want to study, investigate. We have done so many investigations by using the discovery type of things. And then things does not end here. As I told, it's a multi-channel. So you see the 355, 532 signal. And in this signal, that you see the boundary layer and the cloud sitting over boundary layer. So what you see here, the red patches, this is a cloud. And this, what you will see, this blue one, first I will move it like that. You can see this is a boundary layer variation over Ahmedabad. It's a 24-hour. Okay, this is boundary layer variation. This is at 532. This is boundary layer variation. Same time, everything is same. And this cloud is sitting over boundary layer. So beauty is like that, when the boundary layer is going up, then cloud is also following it. Cloud is not separating like that. So it is like that you are sitting on the camel. Camel was sitting, and when camel is sent, and whatever the basically variations camel is doing, then you are sitting over it, and that is doing. This is known as a boundary layer cloud. And for that, one of my student is working, and that we have done very beautiful work like that. Cloud below boundary layer, cloud sitting on the boundary layer, and cloud above the boundary layer. What are their characteristics? What are their probability of rain, and how they are modulating the things. So this is again could become possible due to multi-channel Raman lidar dual polarization. So Raman lidar cloud sitting on the boundary layer. That paper has already come. I forgot to write. This paper has already appeared in atmospheric research. This one. Oh, sorry, RSASE. Remote sensing of atmosphere of environment, RSASE. This paper has come recently, I think few months before. So this you can see that boundary layer, and boundary layer importance needed to say, in the winter boundary layer become very shallow, and that's what the major problem in Delhi region comes due to increased pollution, Ferrari burning, and the shallow boundary layer. So all the three things are together. That's what the Delhi region becomes the gas chamber, because boundary layer never ever goes above 1 kilometer during the winter time, and during night time, or you can say when there is a fog, then boundary layer is at as low as 500 or 700 meter. That paper also soon will come. We are operating lidar from Delhi Earth Station. So that basically boundary layer is shallow, packing volume reduced, everything is pumped, but it is not allowed to escape due to the capping of the boundary layer. So pollution increases and boundary layer becomes shallow. So number increase and the packing volume reduce. So it becomes very, very, very dangerous atmosphere, and that you are seeing every day in the news. Needless to say, you all know it that. And this is again very close to heart. This is the discovery from Indian side and using the Raman lidar. So that you can say this paper came in GRL 2020. Of course, we wanted to put in science, but as you know that our student always wish to publish as soon as possible. So this you see, this is our inset. This is inset satellite picture. Here you see that these are cirrus cloud patches, and this cirrus cloud is like that, as big patches you can see, starting from that Indonesian region, and is crossing full Indian Ocean, and then from Arabian Sea they are just like terrorists, they are intruding into the India. So this is a patch from this one, and then for closer view with more resolution, this is meteosis. So use the same patch, same time it is meteosis, color coded. This is how they are entering into the Gujarat or Western Indian region. These clouds were intruding, and these are the cirrus cloud. And here, that like in the cirrus cloud, we have investigated the so many things, but the most important thing which we established first time in the world, I can say in paper itself it is the first of its kind in the world, that the wave which are generated in the lower atmosphere, mostly gravity wave, these gravity waves are modulating the shape, size and behavior of the ice crystals in the cirrus clouds, and due to the shape, size and behavior changes in the cirrus cloud, the radiation balance is being affected. So that is a punchline of that the discovery thing. No one has looked into this way, whether these waves can modify the ice crystals shape and size and their behavior, and due to that the short wave reflectivity get modulated, and due to that there is a change in the radiation balance. And there are so many other things has been done in this paper, though short, but their supplementary material is I think 7-8 pages, 4 pages GRL paper, and supplementary material is very big. So that is basically using our Raman lidar. Then we did not stop there itself. As you know that we studying the boundary layer very, you can say, precisely, numerically, and all the dynamical things for boundary layer. So this paper, atmospheric boundary layer over Ahmedabad, has come in the AR in 2022, just 2 years before, and that you can see that over Ahmedabad how the boundary layer is changing day to day, month to month, season to season. These are first of its kind result from Indian region using the ground based lidar. And in that, what happens during the onset of the monsoon, active monsoon and withdrawal of the monsoon, this also we have attempted in this, and that has been appreciated a lot by so many readers of this our paper. We still receive the so many requests, and these things, how these things, and the winter, summer, and all the things has been done. And this paper even got the something in Times of India. I have not put here that it was in national news for this one. And then unless, as I told that we work for society, our job is incomplete. So I don't want like that COVID again should come, but the COVID came, and it was basically sad and painful for many of us. During that period also we operated our systems, and this is from ceilometer lidar, not from Raman lidar, and our ceilometer were operational. We were taking permission and were going to clean our systems and to make them upright. And during COVID we have studied the boundary layer over Ahmedabad, and this you can see that COVID-19 period when there was, and exactly same date you can say, just I have put one, there are many dates are there, 2nd April 2019 when there was a no lockdown. This is when there was a national lockdown, 2nd April 2020. You may remember that for first phase was for 7 days, and then it was extended for 14 days, and so it was complete middle of the second you can say lockdown announcement from 1st April to 14 April. And then you may remember during the second phase of the COVID, the government of India did not put the national lockdown. It gave the power, or you can say the permission, to the states. They can put the restrictions. So as I look, no lockdown, national lockdown, and state restrictions. So you can clearly see the state of the boundary layer over Ahmedabad during the no lockdown. You can see the how boundary layer was, how the dynamic boundary layer was there, and you can say box is fully full, and you see that box is fully empty. Boundary layer was not fully developed as it should be. Almost the data is same, everything, zenith angle, everything had been taken care. And then when there were restrictions, you see this is again it behaving like, you see this one and you can see this one. The structures are same, but of course there was a state restriction. People were having fear, they were not moving out. So this type of things, and this also again has come in the several papers and in covered by newspaper Ahmedabad edition. So this by using our lidar. Then yesterday I took an opportunity again. I will thanks to IIRS, RP Singh ji and Saji Kumar ji. So this was basically yesterday's picture. So if I would have given online, then I think I would have missed to explain these things, what is a very important for Dehradun region. So cloud cover over Dehradun region here, just I have not taken just simple picture from my camera is very simple, but you see this, I was sitting on the plane, took the window seat, and then this is when it was about to land to Dehradun. That's what I am saying is the Dehradun region. You see this was the top of the cloud, and then you see that this one is like valley type of thing. This was when it came closer, then I took that quick shot of the picture. This is a valley, and I wish to explore this by using the lidar and Raman lidar, because the water vapor content cannot behave like this, because water vapor is full all the side. It is like well has been digged like that. If we investigate, if we have some, of course I will try by satellite and all these things, this type of things like that. If we have Raman lidar, we can see that how this type of structures are formed. These are not very often. I take the pictures, and from satellite pictures, this you see from all the side, it is just like well, and this well is like that, fully it is transparent. So all the side there, water vapor cannot behave like that. Water vapor is there, and it is this side it is forming the cloud, this side is forming the cloud, and it is just like I'll say that planetary system, that craters are there. So in the cloud there are craters. So I will name like that. This is yesterday's our little effort, and I will work further on that. These are the with the association with all of you. This is a crater in the cloud cover over, and that yesterday you see it is drizzling also, and since yesterday the weather of this place has changed. So this may be having the relation to the definitely it will give the something which is unique to the science, sudden change, and that this type of craters are forming the cloud. These are not very common. Okay, so that is just I covered yesterday, and I thought it will be good for you all who are listening. It will be good, and this way the research progresses. And then this is not related to Raman lidar again, I'll say, but this is a PRL's, DOS and ISRO's initiative in India, that our government's motive is like that, make in India. Everything like that should be make in India, but still we are not focusing like that, observe in India. We are always on many models for many satellite calibration. We are dependent upon the IRA, interim and model simulations for calibrating our satellite sensor, for our training our model, estimating our model. Because why we are doing it? Because we do not have enough observations over India, and that also systematic and graded observation, because we need this type of grids to be filled by the observation from Indian region, and we do not have. And for this, PRL-ISRO has taken initiative, and I am a lead in that one, that is Indian LIDAR Network, ILIN of India. And one node is very much here. I am thankful to Dr. Prakash Chauhan ji and to Dr. R.P. Singh, Present Director ji, for giving all the support for running since last 3 years, a little over than 3 years. The results are going to come. One node is in Dehradun, that is Himalayan Foothill Station. That a very unique station, and it will give beautiful result, as I have shown you that from top of the cloud, and that we are continuing. We request your support, and for this, you see, we have already put about 14 stations, and these stations are there starting from Leh, then you are coming that Dehradun. So Leh, Dehradun, Lucknow, Gorakhpur, Shillong, Dibrugarh, then Indore, then this is Goa, sorry, this is Ahmedabad, Mount Abu, Udaipur, this is Delhi, and these basically two. This one we are going to put first week of January, and Hyderabad we are going to put next week. So Hyderabad NRSC and Jammu region. This we are just going to put next week, within 2 weeks, because system already has reached there. So that way we will be completing the 14 states and 14 stations. And of course our wish is to every state should have that observation, and this grid should be as full as possible from India, observed in India. And for that we are putting effort with the help of all our collaborators, and mostly our collaborators are from ISRO centers and DOS centers, and of course the universities and IITs are with me. And the basic motive is to train our models from Indian soil and to calibrate the sitting sensors over the EOS satellite, Earth Observing Satellite, and for whatever future satellite we are planning in that, for their calibration and their validation, that it should be validated and calibrated from Indian soil by ground truth observation. And my dream is like that, to make more and more observatories which are co-located, having the different system for physical, chemical characterization of various processes into the atmosphere using different tools and technique, whether it is Raman technique, relay technique, or Raman spectroscopy, or so on. And with this, I will say that is possible only in the collaborative mode. CC bond, carbon-carbon bond, I will not say, is a collaborative and campaign mode. Unless we collaborate, this type of studies and this type of successes are not possible. So I am thankful to all my collaborators, all my mentors, and again to IIRS, Dr. R.P. Singh ji and Sefali madam, and this for giving me this opportunity to share some of my ideas and work what we are trying to do from India using the Raman LIDAR and different type of LIDARs over Indian soil. With this, I will say thank you very much. Way forward is like that. We have to be like this, satellite observations, chemical analysis, modeling, and of course, nothing completes unless you have the ground-based observations. So these all are interlinked. Everything is required. Thank you very much for kind attention. If there are any questions or many questions, I will be happy to answer. Thank you. Anytime contact the IIRS team, and they will, I think, get you connected or get your problem solved from. Yeah, sorry. Spectrum to analyze the atmosphere. Yes, basically that is very nice question, Irfan ji. The question is, you says that how the Raman spectrum. Basically, Raman spectrum, what it gives, it is specific to the particular species, like nitrogen. If you take nitrogen, if you illuminate with the wavelength of 355 nanometer, then the Raman line or Raman scattered Stokes line will come at 385 nanometer. So if you are able to track 385 nanometer, then you are sure only you are collecting the signal from nitrogen. So that way you can get the density of the nitrogen. Same wavelength 355 is basically hitting the water vapor, H2O. What is the water into the atmosphere? Water vapor. And water vapor will give the line at 408 nanometer. So whatever signal you are receiving at 408 nanometer, that gives the concentration or characteristics of water vapor. So you have one probe and several detections. So by that way you can study the different species. That is a Raman spectrum. As I showed you, you can see in my slides that I showed oxygen, nitrogen, water vapor. Only I have shown 3. Why 3? Because their number density is enough to get useful signal. Other species are less in the number. That's what their signal may be very weak, but you will get the signal from other species. And you can say the Raman spectrum you will get from other species also, but the signal to noise ratio will be poor, so detection is a difficult. But the species which are larger or higher in the number in the atmosphere or anywhere, you can get enough signal to detect them quantitatively. So hope I have answered your query. And then next one is what is the purpose of green laser on a laboratory observatory? Basically, beggars are not choosers. Nd:YAG laser, it is a most sturdy laser, most you can say trouble free laser, and it comes from Nd:YAG is a neodymium yttrium aluminum garnet. The crystal name is Nd is neodymium crystal, it is yttrium aluminum garnet. Nd:YAG stands for neodymium yttrium aluminum garnet, and the fundamental lasing wavelength or laser wavelength of Nd:YAG crystal is 1064 nanometer, and 1064 nanometer comes in the infrared range, and detecting infrared range is a difficult because it gives the heating effect. So detectors limits us to detect at 1064, and alignment becomes very difficult because we cannot see the IR. So then what we do, we double the frequency of 1064. When you double the frequency, then wavelength become half. So if you 1064, if you divide by 2, it becomes 532, and 532 is clear crystal green laser. So that's what, and green laser is easy to align. And very important scientific thing I would like to tell you, our purpose is to receive maximum signal, and that signal, when we will get the maximum signal, when it is not absorbed into the atmosphere. Suppose we pump laser and it is absorbed by the ozone, it is absorbed by oxygen, it is absorbed by nitrogen. So while going it will be absorbed, and when the backscatter signal which is very weak, it will be again absorbed, we will not receive the signal. But the green light 532 is least absorbed into the atmosphere, and that is proven because if you see from the sun, the maximum light comes at 555. The maximum light around yellow it comes na. So that means why maximum light comes at 555, because it is least absorbed. So if we pump at 532, then the backscatter signal will be least absorbed, so our signal to noise ratio will be very, very good. And that is the purpose of choosing. There are two purposes, as I told, choosing. One is a scientific, another is a limitation of the technology. So that is a 532. Then Lalita ji has asked, so for complex molecule there could be many signal and create noise in signal, how to overcome this? Yes, you are very much right, and that's what our scientists and technicians job is there, to work in the complex situation. If the stream is road is very straight, then like that our job becomes very simple. But we don't want to make our job simple. These things are like that. Almost we try to like that complexities how to resolve the complexities, and for that we are having the multi-probe. Multi-probe means simultaneous observation. Suppose the situation is not resolved by one wavelength, then we try to look that into another wavelength, then third wavelength, then we try to look from satellite, and then we try to look like that. That time we'll try to fly the balloon in situ also. So we try to employ the simultaneously the different tools and techniques, different platform, and try to resolve the complexities as many as possible. But as you know, everything cannot be resolved. Then Ria is asking, sorry? Acha, Prince Kumar, how do the optical characteristics of atmosphere molecules such as Raman scattering cross section and fluorescence emission spectra vary with the atmospheric pressure and temperature, and how do these variation impact the interpretation of data at different altitude? A very good question. Basically these molecules, atmospheric composition and all these things. So the total density changes. This physical process, total density is distribution. As you go up, the density decreases and then pressure decreases. But due to this vacuum and all these things, our signal becomes more clearer because the lines become less contaminated. So it is basically blessing in disguise. Okay, I'll say that it is useful for us, and the cross section and these things are basically not modulated by that. Only shape and size, which is a physical parameter, that is depend upon the pressure and you can say this altitude. But that this molecular size, whether it is nitrogen, if you take nitrogen and oxygen composition at 1 kilometer, you will find composition wise, relative composition, nitrogen is 78% and oxygen is 21%. If you go 20 kilometer in homosphere, the relative composition will remain same, 21% oxygen, 78% nitrogen. If you go at 70 kilometer, also the relative composition of nitrogen oxygen will remain same. Nitrogen will be 78% and oxygen will be 21%. Please remember, total number will decrease, number density will decrease, but the relative composition of gases, nitrogen, oxygen, argon, carbon dioxide, these are 4 major gases. Their relative composition is independent of the altitude up to mesopass. In the homosphere up to 80-85 kilometer, this relative composition remains same. Of course, trace gases, they are changing from place to place, region to region and season to season. They are changing. But these parameters are not directly impacting what we are investigating. Thank you very much. If there are any questions and all these things, you can write to IIRS and I will be happy to answer you in writing, because I'll go back, then I can send the mail to them and they can forward. If you have any question later on after seeing my presentation, or you can say after reading my slides, if you have any question comes to your mind, please don't hesitate in asking. Then there will be a proper learning, or proper, you can say, you will learn a lot from today's workshop. Thank you very much for all the audience and to all the IIRS community for giving me this opportunity to interact. Thank you very much.
Some question on you.
Yes, sir. Yes, sir.
Should I go? Yeah.
Thank you, sir, for delivering the interesting and informative talk. Now there are few questions which I would like to answer. Like one question is there: what are the prospects of exploring nanoparticles in sediments of beach with the help of Raman spectroscopy? So if one will be interested, they can take the sample from the beach, and if they will be interested in knowing the amount of nanoplastic, or like how much contribution is there of the nanoplastic, or what is the availability of the nanoplastic in the sediments. So from that sample you can test in the laboratory, and the Raman spectra of the normal sediment and the nanoplastic both will be different, and based on that one will be able to classify the sample, and they will be able to know the what is the total amount of the nanoplastic in the in that sample. And there were few questions related to cancer cells. So I found there were few questions related to that also. So several studies have been carried out to detect the cancer cells in some cases the breast cancer, sometimes by taking the blood sample also, sometimes by taking the urine sample also. So the spectra were generated, and the significant change in the spectra was identified in the normal urine sample and the urine sample of the cancerous person, as well as the cells, the healthy tissue as well as the cancerous tissue when both were detected. So these were the difference in the spectra were difference in the Raman signals were obtained, And the experts, medical experts, they are working to combine with the different techniques, including the Raman spectra, to get the more precise result for the detection of the cancerous cells in the body. How does the Raman spectroscopy contribute to the vegetation health monitoring in the Earth observation? So again, in the Earth observation, when you will take the spectra of the healthy vegetation and the spectra of those kind of vegetation which are suffering by some kind of disease or some kind of problem, so definitely there will be change in the spectra. Based on that, one will be able to find. Like here, even we have seen in the talk, when the samples were taken for the two different tree species, plant species. So now they are spectra were following the similar pattern, but there was different in intensity. So based on that, one will be able to clearly say that these are the the tree leaves or the vegetation leaves from the two different species. Can Raman spectroscopy be used to detect the pollutants in the water bodies from a remote sensing data set? So using spaceborne, it is very difficult, but using airborne, some studies have been carried out. Not from a long distance, 50 meter, 100 meter or 150 meter distance, the sensors were placed to detect the level of pollutants in the water bodies. What role does Raman spectroscopy play in the mineral identification from space? Actually, currently, Raman spectroscopy has not been operated on spaceborne or spaceborne sensors or from the spaceborne platform. But the data set have been acquired by putting those sensors for the in situ measurement. Like on the Mars, the sensor was placed on the rover, and finally the data set was analyzed, and the people were able to find their findings. And one more question was there, I was not able to understand, or sorry, not able to find it here. Like the question was there related to the merger of the Raman spectra of Mars with the machine learning technique. Basically, that was not for the Mars. That was an experiment which was carried out with the Mars-like environment, in which 0% dust environment to 50% dust environment was there, and there they had tried the different machine learning approaches to classify. So using those approaches, the neural network technique had shown the very good result. Now, if you have more questions, so I will be happy if someone has placed on YouTube link, or if those questions are not listed here. So I will suggest you to forward an email to me or to the concerned speaker. So I will be very happy, or to our DLP team, I will be very happy to answer. And now I am thankful to all the audience and the participants who has participated in the in this workshop. So I am thankful for the participants, and now we are going to close this workshop. Thank you.